Hello everyone, I welcome you all to the amazing platform of Physics Wallah. Today we are here to discuss the new chapter which is P block elements. Today we are going to discuss the boron family, and in the next session we are going to discuss the carbon family along with some of the questions and the DPP. I hope you are going to enjoy the lecture and you are going to see the lecture very carefully in the concentration manner. Okay, now when you are starting the P block elements chapter, first of all, one thing you should know that where exactly the P block elements are present in the periodic table. Okay. Now, here when you are talking about periodic table, towards the very left hand side, you people know that there are S block elements. Okay. And in the middle, there are D block elements, and over here there are P block elements, and in the down there are F block elements. This is how your periodic table is divided. Okay. In the P block elements, there are some groups present. There are some groups present which is from 13 to 18. 13 to 18 groups are present in the P block. I have already explained you in the periodicity chapter. So in the 11th standard, we have to study the group number 13 and the 14, whereas in the 12th standard, we are going to study the 15 to 18 groups. So today we are going to start the group number 13 and 14. So first of all, you should know everything about what we have to start today. This is the very short form of the periodic table. This is the very short form of the periodic table I can give you over here. So this whole part is your area of concern, in which group number 13 and 14 we have to start. Okay. So let's start with the discussion. So let's start with the family which is group number 13. So if we are talking about the group 13, first we should know what all elements are present in the group 13. First we should know all of the elements present in the group number 13. So we have over here boron, aluminium, gallium, indium and thallium. The elements present in this respective group is all these elements. Okay. So the first we are writing the name of these elements. We have over here boron, we have over here aluminium, boron, aluminium, gallium, indium and thallium. One more element we have, which is nihonium. All these elements are present first of all in the group number 13. Now we have to write the atomic number of all these elements. Now we have to write the atomic number of all of these elements. Boron is 5, then we have 13, gallium is 31, indium is 49, thallium is 81 and nihonium is 113. This is the atomic number of all of the elements present in this respective group. Okay. Nihonium is a synthetically prepared element because it has been discovered in only 2004 itself. Okay. Now, writing the electronic configuration, if we write the general electronic configuration of this group, if we write the general electronic configuration of this group, if we write the general electronic configuration, general electronic configuration of this group, that will be NS2 and NP1. This is the general electronic configuration of this respective group, NS2, NP1. Now, for all of the elements, if we have to write, we have over here helium, neon, argon, krypton, xenon, and then radon. We will write the electronic configuration including the noble gases. So we have over here 2s2, 2p1. We have over here 3s2, 3p1. We have over here 3d10, 4s2, 4p1. We have over here 4d10, 5s2, 5p1. Then we have over here 4f14 and then 6s2, 6p1. You can write over here D also, 5d10, 6s2, 6p1. And here we can write over here 5f14, 6d10, 7s2 and 7p1. So these all elements are having the electronic configurations like this. One thing is common in every of them. One thing is common in every of them is the last electronic configuration, which is s2p1, which is s2p1. That we need to understand. 5s2, 5p1, 6s2, 6p1 and then 7s2, 7p1. So general electronic configuration I have kept in the box, right? We have to keep in our mind when we are talking about the general electronic configuration. See, gallium I'm having 1 star and thallium I'm also having 1 star attached. You always have to remember the electronic configuration of these two elements very nicely, because you know there are so many exceptions related to this respective group with respect to the gallium and thallium elements. So remember the electronic configurations, right? Nihonium. Okay, first of all, some other important things related to this respective group. These all are the electronic configurations. Now the next thing is boron is a non-metal. Rest all of them are metal. Rest all of them are metal. So it's very easy for you to remember the nature of all of the elements of this respective group. Now I will write over here that nihonium is a synthetic metal. It is a synthetic metal. As you know that it is prepared artificially. It has been prepared in the recent years. It is not like discovered a very before time. Okay, so it's a synthetic metal. It's a man-made metal. You have to remember all of these things with respect to this group. Okay. Okay. So first of all, I have just written the electronic configurations. As you are in the class 11 standard now, okay, you should know first of all the general electronic configurations of all the elements, and for that, if you are not knowing, you should follow the chapter which is the structure of atom. Okay, perfect. Group 13 elements. Moving towards the next part. Now we have to understand the properties. Now we have to understand the properties of all of the elements of this group. Now we have to understand the properties. So when we are talking about the properties, first of all we have atomic size. First of all we have over here atomic size. Now as you know that when we are moving from top to bottom, size increases because there is including shells, because when we are moving from top to bottom we have adding of the shells, right? Let's say you have boron, aluminium, gallium, indium and thallium. So you will expect that when you are moving from top to bottom, your shells increases, right? You will write over here that number of shells increases, so normally we can say that size increases. We have studied this, all these things in the periodicity chapter, that when you're moving from top to bottom, your size will increase. Okay, perfect. But you know, the exact order of the size is not what is from top to bottom written on the blackboard, that it will increase. The exact order of the size over here is boron, gallium, aluminium, indium and thallium. This is the correct order of the size. Yes, it is following the simple concept of that there is increase in the number of shells when we are moving from top to bottom, but solely this is not based on this factor, because as you can see, there are some exceptions present over here. There are some exceptions present over here. First exception is, whenever I'm writing the exception, I will write the 2 star. Whenever I'm writing the exception, I will write the 2 star. Okay, so you know that the expected size is that gallium should be greater than aluminium because it is having greater number of shells, but this is not correct. You can see that aluminium is having the greater size, gallium is having the less size, and even we can see here also indium and thallium are having almost similar sizes, so this is also not correct. Thallium should have a very big size. Now what is the reason associated with that? First, we should write for the gallium because question is asked for the gallium only. The electronic configuration of gallium is argon 3d10 4s2 4p1. 3d10 4s2 4p1. Now in these elements there are d electrons. D electrons are present. We will write over here that d electrons are present. Okay, and you know that d electrons have very poor shielding effect. It is having very poor shielding effect. It is having a very poor shielding effect. That's why we will have a decrease in the size. Now what is happening over here? See, this is the nucleus and this is your outermost shell. Okay, and we are talking about the size of the gallium over here. Now you know that the shielding effect of S is the largest, then P, then D and then F. This is the order of the shielding effect of all of these elements. Now you know that for the case of D, you know that the shielding effect is very less. In the case of the D, you can see very nicely that the shielding effect is very less. We have to consider this as in our present case. So you can simply say that the effective nuclear charge is very high on the electron which is present in the outermost shell. The effective nuclear charge is very high on the electron present in the outermost shell. The nucleus can attract this electron very effectively because the d electrons are having very poor shielding effect. They are present very down. They are not creating any shield between the nucleus and the outermost shell. They are present down. So the charge of the nucleus can go very easily to the outermost electron. It can attract outermost electron very easily, right? It will attract the outermost electron very easily. That as a result, this will be attracted towards the nucleus. This will somehow, it will shift towards the nucleus. Attraction will shift this respective boundary towards the nucleus. And as you can see, if it is shifting towards the nucleus, your size will simply decrease. Okay, your size will simply decrease, because size decrease is only explained on the basis of the shifting of the boundary of the outermost shell of something inside. And that can only be possible if the nucleus is attracting that respective electron towards itself, so the boundary shifts. You know, there is no exact boundary of the respective atom. Okay, whenever we have to assign the size, we will see where is the point where the last electron is present. That will only be the boundary. If it is shifting inside, so the boundary will also shift, so the size will decrease. Understood, everybody? You have to just focus on the thing that d electrons are present. They have a very poor shielding effect. They will be present down. That's why the protons which are present in the nucleus will attract the outermost electron very effectively. So it will shift its boundary inside and size will decrease. You will see that this respective size will come almost equal to, it will come almost equal to the aluminium. It will come almost equal to the aluminium. That's why we have written the size of gallium and aluminium as almost equal, but aluminium is somehow bigger than gallium, because the reason is that gallium is having the d electrons, but aluminium is not having any d electrons. So due to the d electrons, the shielding effect is poor, the electrons are down, the nucleus will have its effect on the outermost shell, it will shift it inside and the size will decrease. Okay, remember this thing very, very nicely. I have written over here d electrons are present and d electrons are having very poor shielding effect. They have a very poor shielding effect, therefore size of gallium is almost equal than aluminium, but yes, aluminium is larger than gallium. Okay, let's move forward. Next we have the property over here is our ionization enthalpy. Is our ionization enthalpy. Now let's talk about ionization enthalpy. Now you know that ionization enthalpy is simply the energy required to remove electron from an isolated gaseous atom. From an isolated gaseous atom. Energy required to remove electron from an isolated gaseous atom. Okay. Now, remember, we have over here boron, aluminium, gallium, indium, thallium. Okay. You will expect that when you are moving from top to bottom, your order of the size is something like this, which is boron, gallium, aluminium, indium and the thallium. Okay, almost the size order is this. Okay, so you will expect that the order of the ionization energy should be opposite of that, because you know that ionization energy is inversely proportional to the size. Ionization energy is inversely proportional to the size. You can see this order very nicely. You have studied this order in the periodicity chapter itself. You have studied this in the periodicity chapter. So you will simply write the order of the ionization energy. You will write that it will be highest for the boron, then gallium, then aluminium, then indium and then thallium. We are writing this order because we know that the ionization energy order is exactly reverse of the order of the size. We are writing this order on the basis of this only, Okay, now this order actually is not correct. The correct order of the ionization enthalpy is boron, then we have thallium, gallium, aluminium and the indium. This is the correct order of the ionization enthalpy, and you can see very easily that this thallium is creating a very big exception and even the gallium is also making exception. Already we have included the exception of gallium in the size order, but still it should not be present here. Okay. So we have the order of the size like this. We are thinking that ionization enthalpy is the reverse of the size. So we are just making the reverse like this. But still this is not the order of the ionization enthalpy of the boron family. The exact order is this. Now why it is present like this? Now we have to understand. Okay. Now, till here, boron, gallium, aluminium, indium, you can answer that yes ma'am, the size order is like this. So obviously ma'am, ionization enthalpy order is applicable to everything except thallium. Ma'am, what is the problem with the thallium? Why thallium is having the biggest size? Why thallium is having the biggest size but the ionization energy is coming after boron? What is the reason? That reason is present in the electronic configuration of the thallium. So first of all, we have to write the electronic configuration of thallium. That is xenon, and we have 4F14, 5D10, 6S2 and 6P1. This is the electronic configuration of the thallium. Now, when you are filling the electrons in the thallium, you are having the outermost electronic configuration like this. Okay. So you have filled 4F, 5D, 4D and 3D. You have filled all of these respective subshells in the thallium. Like when you are writing the electronic configuration, you must have written the 3D10 also, you must have written the 4D10 also. Okay. And now we have fully filled 4F14 and then 5D10. All of these respective subshells are already filled while writing the electronic configuration of the thallium. Okay. Now, 4F is having the 14 electrons, 5D is having the 10 electrons, 4D is having the 10 electrons, whereas 3D is having the 10 electrons. And we have over here 44 electrons. How many electrons? 44 electrons. Now, all these 44 electrons have poor shielding effect. I can write over here that all these 44 electrons have very poor shielding effect. I can write this, very poor shielding effect. Okay. Okay. They are not creating any repulsions. They are not creating any repulsions. 44 electrons, 44 electrons. Obviously, you know that these are D and F electrons. Obviously, you know that these are D and F electrons, and that has very poor shielding effect. Okay. Which has poor shielding effect. We have 44 electron which has poor shielding effect. Okay. Now, what will happen that when you have 44 electrons which have no shielding effect, or I can say they have almost poor shielding effect, how it can change your ionization enthalpy? Now understand. You have a nucleus over here and I am talking about the thallium. This is the boundary of the thallium. This is the boundary of the thallium. Now, S, P, D, F. We have D and F over here. Okay, this is S and P. We are not talking about the S and P. We are talking about the D and F. Okay. Now, D and F. Total electrons are how many? 44. In the case of what? Thallium. So, I can say that 44 electrons. I can say that 44 electrons have the poor shielding effect. So, all these 44 electrons are present over here. Okay. And they are creating no shielding, they are creating no repulsion. So, the nuclear charge can very easily travel to the outermost electron. It can easily travel to the outermost electron. First of all, 44 electrons are present in the D and F respective subshells or the orbitals, you can say. And they are creating no shielding effect. They are creating no repulsive interaction. If this is nucleus, this is the outermost shell. They are present very down. Okay, they are not creating any kind of a wall in between. They are not creating any kind of a shielding in between the nucleus and the outermost shell. Okay, fine. But since you know that 44 electrons are not creating any shielding, but there are 44 protons present in the nucleus which have the ability to attract this respective outermost electron. Electrons are not creating any kind of a shielding. They are present very nicely. They are simply sleeping between the nucleus and outermost shell. They are very down. So the nuclear charge is effectively applicable on the outermost electron due to the 44 electrons. Okay, due to the 44 protons. So what will happen? The size of the thallium will not decrease. Size of the thallium will not decrease because, you know, in the case of the thallium, shell number is also increasing, because some of you might think, ma'am, if 44 electrons are having so much poor shielding effect, so why the size of the thallium is not decreasing? Because we have a barrier of the shells also, hai na? There is a shell number present. Okay, so the shell number cannot change, so you cannot decrease the shell, the size of the shell. The shell size is almost in everywhere the size of the shell is same. Okay, it will be constant. So the shell number cannot be changed. The thallium last electron will be present over here only. But with this nucleus, it will have a very high attraction. With the nucleus, it will have a very high attraction. It will attract the outermost electron very effectively. So the removal of this electron will become very, very hard. It is creating so much of attraction, the nucleus is creating so much of attraction that it is trying very, very hard. It is trying very, very hard to, you know, to attract that electron towards itself. The case similar to the gallium, but it is not able to do because of the shell size. But you know that they are trying level hard to attract that electron, so the removal of that electron will become very, very hard. It's like this is the last electron of the thallium, it's pulling it towards itself. This is the nucleus, it's pulling towards itself, but it cannot move. It cannot move because there is a barrier of the shell present over here. I cannot move beyond this line. Okay, but I'm so much attracted. I'm thallium, I'm the last electron of the thallium. I'm so much attracted towards this nucleus that if any energy is given to me for the removal of the electron, it is very hard, right? So this is the reason. After the boron, thallium is coming because thallium is having D and F both electrons, so that is having a very poor shielding effect. Their removal, the last electron removal in the case of the thallium, is very, very hard. Is very, very hard, right? So all of these things you have to remember. I'm not writing all these things. This is only for your understanding. Now I'm removing all these things. I hope you people have understood. You can write this in your notes, but anywhere you can make a box and you can write. This is only for the rough purpose. Okay, this is only for the rough purpose. Now D and F electrons have poor shielding effect. D and F have poor shielding effect. D and F electrons have very poor shielding effect. Very poor shielding effect. That's why last electron of thallium is tightly attracted towards nucleus, and its removal is hard. I think this is clear to everyone. Always remember that it's not always mandatory that if you have a very poor shielding effect, you will always have a decrease in size. Sometimes you might have decrease in size, sometimes you might have change in the other property, maybe ionization enthalpy, maybe something else also. We will discuss the inert pair effect also in the present case after some time. So you will have so many properties changed because of the shielding effect, which is poor because of the D and F electrons. That is not the case that always the effect will be on the size itself. Okay, now let's move forward. This is the case of the ionization enthalpy. Now let's move towards the melting points and the boiling points. If you talk about the melting points, we are having so much exceptions in this respective group. The order of the melting point is this is the order of the melting point in the group 13 elements. And for the case of the boiling point, it will be simply like this. Simply it will be like this. It will be highest for the boron and least for the thallium. Even you have to remember that this boron is present as B12 icosahedral shape. Not required to learn, but you should know. It is a giant covalent. It is a giant covalent molecule, and it's having a very high melting point. It is having very high melting point. So you have to remember the order of the melting point and the boiling point in the case of the group number 13 elements. Now the next case over here. Now we have to discuss the oxidation states. Now we have to discuss the oxidation states of this respective group. Oxidation states. And it is very important to understand what is happening in this respective topic, oxidation states. Now, we have our boron family. We have our boron family in which we have elements as boron, aluminium, gallium, indium and thallium. General electronic configuration of this group is ns2np1. So S is having 2 electrons and P is having only 1 electron. Let's say if I excite also. So how many number of unpaired electrons I am going to get? How many number of unpaired electrons I am going to get? Only 3. So the oxidation state possible over here is +1, whereas oxidation state possible over here is +3. +1 and +3 oxidation states are possible. +1 and +3. Okay, no problem. After that, if we have all of these elements, after that, we have to answer one important thing, that oxidation states possible are +1 and +3. But if I ask you the stability order for all of these, so you will get to know that there is very exceptional order. All of these elements have +3 oxidation state as the most stable one, whereas only thallium have the lower oxidation state as the stable one. Now, why this happened? Why there is an exceptional order in the case of the oxidation state in the case of the thallium? Why thallium is more stable in lower oxidation state? First of all, I am telling you the fact that there is a possibility of the +3 oxidation state in this respective group, +1 oxidation state in this respective group, but the order of the stability of the oxidation state for all of the elements is like this: +3 and +1. For some of them, +3 is more stable, for some of them, +1 is more stable. And thallium is very, very exceptional. Now, this happens due to the effect which you have to study over here, which is the inert pair effect. Now we have to study the inert pair effect. Now what is inert pair effect? Listen very carefully. What is inert pair effect? It tells you that reluctance of s electrons to participate, reluctance of s electron to participate in the bond formation. Reluctance of s electrons to participate in the bond formation. Now this is the definition of inert pair effect. Okay. Now what exactly it is? For the last element, stability of lower oxidation state, is more as compared to higher oxidation state. For the last element in the group number 13, 14 and 15, it is applicable. So for the last element, the stability of the lower oxidation state is more stable as compared to the higher oxidation state. Now these 2 points are coming under the inert pair effect. Reluctance of s electrons to participate in the bond formation, and for the last element, stability of lower oxidation state is more as compared to the higher oxidation state, So we can simply say over here that for the thallium, +1 is more stable as compared to +3. And because of this reason, thallium +3 is always accepting 2 electrons and it wants to become thallium +1. So by chance, if you have thallium +3, it will always behave as oxidizing agent. It will always behave as an oxidizing agent, because you know that the oxidizing agents are the one which reduces itself and oxidizes others. So it will reduce itself from thallium +3 to thallium +1. Always, if you have the last element in the higher oxidation state, it will always behave as an oxidizing agent, because itself it will reduce. Okay. So these are the points for the inert pair effect. Now why this happens? Now understand. Reason. Now understand the reason. When we talk about the thallium, it is the last element. Okay? It is the last element of this group, which is having the electronic configuration as xenon, 4f14, 5d10, 6s2, 6p1. This is the electronic configuration, right? Now, this is the nucleus and this is the outermost shell. Okay, this is the outermost shell. Here we are having 6s2 and 6p1. Let's say sixth shell is the outermost shell. So first s electrons are present and then p electrons are present. Okay, this all is present in the sixth shell, right? Now, you know that in the case of the thallium, we have a very poor shielding effect of the D and F electron. There are some electrons, there are around 44 electrons of D and F. I have already explained you before, 44 electrons of D and F which have poor shielding effect, which have very poor shielding effect, which have very poor shielding effect. So the charge of the nucleus, is going very effectively towards the outermost shell, and it will bind the electrons of S towards itself. Like the rays are going towards the outermost shell, which is coming first. S electrons are coming first. So it will tightly hold the S electrons. This is the hold. This arrow I have made is the hold. So it will attract tightly the S electron. It will hold tightly the S electron. So p electrons are present. After that, so the removal of the p electrons is easier. This one electron will participate in the bonding. For the thallium, this one electron will participate in the bonding. It will be used in the chemical reaction. There is a problem with thallium, that for the thallium, the last shell, the sixth shell, 2s electrons are very tightly held by the nucleus because of the poor shielding effect of the D and F electrons. Okay, beta. So I'm writing over here. That effective nuclear charge which is the Z effective, is present or applicable more to S electrons as they are closer to nucleus as P as compared to P as compared to P. Effective nuclear charge, which is a Z effective, this is the charge of the nucleus on the outermost shell, is present or applicable more to the S electrons as they are closer, because you have to see first S is present, after that P is present. So the hold of the nucleus is more on the S electrons. They will not participate in the bonding. What I have written over here? What is the definition of the inert pair effect I have written? That you have to see. Reluctance of the S electrons to participate in the bond formation. Reluctance of S electrons to participate in the bond formation. For the last electron, stability of lower oxidation state is more as compared to the higher oxidation state. And you can see, always if you have the higher oxidation state, you will be behaving as an oxidizing agent. Okay. And I have explained you the matter over here. So you can simply see that for the thallium, if only p electrons are involved, so +1 oxidation state is stable. This is all for the inert pair effect. Okay, I have explained everything to you regarding the inert pair effect. So you have to remember that whenever you have a thallium I3, it always dissociate to give you thallium +1 I3 -1. This is a very famous reaction which gives you an inclination of the inert pair effect. Okay, they can ask you the shape also of this respective compound I3 negative. This is a linear shape. This is also of the linear shape, which is having the hybridization sp3d. It is of the linear shape having the hybridization as sp3. So everything I have explained you with respect to the inert pair effect, and you don't have to forget. You don't have to forget any of these things. This is very, very important. Okay, beta? I think you people have understood. Now, next thing. Next we have electronegativity. See, these are the values of the electronegativities of all of the elements. You just have to remember the order, which is highest for the boron, then thallium, indium, gallium, and aluminium. This is the order you have to follow. Only remember the order. Only you have to remember the order. It's not required that you need to remember the values, but only remember the order. Boron and aluminium. Boron and aluminium have difference of electronegativity as 0.5. Difference of electronegativity is 0.5 for the boron and aluminium. Sometimes this question can also be asked. So you have to remember this very nicely. In this respective whole of the elements, maximum electronegativity difference they are having. They are having the maximum electronegativity difference they are having. Okay, so this question can also be asked. Remember nicely. And even I can include the order of the density also over here. I'm including the order of the density over here. Order of the density, which is boron, aluminium, gallium, indium, thallium. This is simply because mass is increasing top to bottom. Mass increases top to bottom. Nothing else we need to do over here. Simply mass increases top to bottom. This you have to remember. This only you have to remember. I think this is clear to everyone. I think this is clear to everyone. Okay. Now, the next thing we have to do over here is the reaction. Now we have to do the reactions. Okay. You know, boron reacts with air. Boron have a reactivity with air to give you some important compounds. How they react? Any of the element of this group is having oxidation state as +3 and oxygen has -2. So if you will react, you will get the element as M2O3. You will get the element as M2O3. You will get the element as M2O3. So B2O3, as boron is a non-metal, you will get the acidic oxide. Aluminium is having the amphoteric oxide along with the gallium. You have to remember this. You have to remember this very, very nicely. You have to remember this very, very nicely. Gallium and aluminium oxides are amphoteric, while rest of them are basic. While rest of them are basic. You have to remember always. And even if you want to have the reaction with the nitrogen also, you can simply have, for the nitrogen you can have that M is having oxidation state as +3, whereas nitrogen is having -3. So you will have Mn as your compound. So you will have Mn as your compound, M2O3 and Mn. Okay. Now, there is one more important point, that B2O3 is also called as boric anhydride. Okay. What does it mean? If you react B2O3 plus water, you are going to get H3BO3. You are going to get H3BO3. B2O3 plus water, you are going to get H3BO3. Okay. Now, this H3BO3 is called as boric acid, or you can simply say orthoboric acid. It is called as boric acid. It is called as the boric acid. H3BO3 is called as the boric acid, and B2O3 is called as the boric anhydride. It is called as the boric anhydride. Now, what is an anhydride? Anhydride is something It is a type of an oxide in which if we dissolve the water, you are going to get the acid. It is a type of an oxide in which if you are going to dissolve the water, you are going to get the acid, which is the boric acid. So boric anhydride, when reacts with water, you are going to get the boric acid. These all things you need to remember. Acidic oxide, amphoteric, basic, what it is called, what is the acid you're going to get, how you're going to get the compounds. All these things you need to remember. Even you have to understand the reactivity with the bases. Reactivity with the bases. Now I ask you a question, that in all of the elements present in the group 13, what are the elements which are not going to react with the bases? The one which forms the basic oxides. So which forms the basic oxides? You know that indium and thallium, as they are metals, so they are going to form the basic oxide. So they don't react with bases. They don't react with the bases. Okay, beta? I hope you people have understood. Now, if they react, what they are going to get? Like, for example, if I have aluminium, I react that with NaOH. What you are going to get? You are going to get sodium AlOH4. You are going to get this respective compound, and along with this, you are going to get the hydrogen gas. This is the reaction you are going to get. Okay? This is the reaction you are going to get as a result. And even there is an application also. This hydrogen gas is used to open the blockage in pipes. It is used to open the blockages in the pipes, this hydrogen gas. Okay, because it is coming with a very high pressure, it can use to open the blockage in the pipes present around us. Okay, so you have to remember the reaction with the bases, and only one point is important, that which all elements are not reacting. Reaction is easy, we can easily identify, but this is more important, that indium and thallium does not react with the bases. Now moving towards the next, which is reactivity with the halogens. Which is reactivity with the halogens. Reactivity with the halogens. Now, whenever you have element M reacting with any of the halogen, you are going to get the compound which is MX3. You are going to get the compound which is MX3. Okay, because of the valency concept. So the compounds you are going to get over here is BX3, ALX3 and gallium X3. Similarly, you will have the indium X3 and the thallium X3. So these are the compounds you are going to get. Okay. Now, what are the questions which can be asked to you with respect to this? Now you have some of the acids like BF3, and then we have BCl3, BBr3, Bi3. Okay, we have all of these respective compounds of the boron with all of the halogens. When we are moving from top to bottom, they will ask you the Lewis acid strength. They are going to ask you the Lewis acid strength when you are moving from top to bottom. Now, some of you might think that the Lewis acid strength top to bottom decreases. Why? Because when boron is attached with the fluorine atom, it is having a very high electronegativity, That's why boron is having a very high electropositivity. This boron is very highly electron deficient, very highly electron deficient. But in the case of the iodine, but in the case of the iodine, iodine is having a very, very less electronegativity as compared to the fluorine. So it will not attract much its electron density, the electron density of the boron iodine bond towards itself. So this boron will not be very much electron deficient. Okay, so this is the most of the students think in this way. So I am telling you what you people will think, that when you are moving from top to bottom, your tendency of being the electron deficient, because Lewis acid strength uh, order is decided on the basis of which boron is most electron deficient. Okay, I will write this also. Decided on the basis of decided on the basis of most electron deficient boron, most electron deficient boron. So you will think that most electron deficient boron will be the one which is present in the BF3. But I should tell you the order is reverse. When you're moving from top to bottom, your Lewis acid strength increases. That means that this boron is the most electron deficient. This is the most electron deficient, and this is in this respective case least electron deficient. We are talking in the relative manner, least electron deficient, most electron deficient. Okay, now why this happens? Now understand the reason. Now understand the reason why it happens. See, boron is having electronic configuration as 1s2, 2s2, 2p1. This is the electronic configuration of the boron. Okay. Now, when you take the boron in the excited state, it will be 1s2, 2s1, 2p2. So, one box is present with the s electron, and then p will have the other two electrons. This is 2s and this is 2p. S electrons and the p electrons. Okay. Now, you will see, I should make it in a beautiful way. This is 2p. Now you know that this respective orbital is empty. You know that this respective orbital is empty. It's not having any electron. Now what happens? Now what happens when the boron is forming compound with the fluorine? It is represented like this. Now one of the p orbital which is present on the boron, one of the p orbital which is present on the boron is empty, and fluorine is having these much electrons present. These much electrons present. Okay, one electron of the fluorine is involved in the bonding with the boron, and rest of them are present as a lone pair. So what happens that these two electrons can be back donated into the empty orbital of the boron. I will write over here the lone pair of electrons on fluorine can be back donated to boron, can be back donated to the boron. Now the electron deficiency of boron will be decreased. Now if fluorine is giving electron density to boron, so it will not feel any kind of electron deficiency. What happens in the case of the iodine? Now what is happening in the case of the iodine? Iodine is also having the lone pair of electron, but you know there is a difference. There is a difference. Now what is the difference? I am telling you. Understand. Now what is the difference? I am telling you. I will compare all of these compounds. I will compare all of these compounds. Now, boron and fluorine are having the size order like this. And in the case of the boron, chlorine, the size order is like this. While in the case of the boron and iodine, the size order is like this. Okay, I should make it over here. In the case of the boron and iodine, now you will be able to understand. Now you will be able to understand. This respective overlapping is the 2p 2p overlapping. This is 2p 3p overlapping. This is 2p and 4p overlapping. Now, according to you, I have explained you in the chemical bonding chapter also, this filled electron density on the fluorine, on the chlorine and on the iodine, this can be back donated easily. Here I can write over here that back donation is effective, easy, or you can simply say effective. Back donation is effective as 2p 2p overlapping, as 2p 2p overlapping is effective, as 2p 2p overlapping is effective. Here you are having the overlapping as 2p 2p. Here you are having the overlapping as 2p 3p. And here you are having the overlapping as 2p 5p. Here you are having the overlapping as 2p and 5p. So when you are moving from top to bottom, effective overlapping decreases. Effective overlapping decreases. I will write over here that when we are moving from top to bottom, effective overlapping decreases. Back donation decreases. Back donation decreases. Okay. I hope this is clear to everyone. Back donation decreases. So iodine is not able to back donate the electron density into the boron, whereas fluorine can easily back donate the electron density to the boron. So I can write over here that why the Lewis acid strength is like this. Iodine cannot back donate to the boron. Boron is still electron deficient. There is no electron gained because of the iodine. But in the case of the BF3, fluorine can back donate the electron density to the boron very easily. So it will have very good electron density present in the empty orbital also. So it will not behave any of the electron deficiency. So it will not behave as a Lewis acid. So Lewis acid strength increases when you're moving from top to bottom, and that means that which boron is the most electron deficient. This is a very, very important question. I have explained you in the best manner I can. Now, one more question can come from here. That is aluminium fluoride, aluminium chloride, aluminium bromide and aluminium iodide. We have all of these respective halides. In all of these, aluminium F3 is considered as the ionic, while rest of them is considered as the covalent compounds. Rest of them are considered as the covalent compounds. And even AlCl3 in the solid phase or in the liquid phase is considered as the Lewis acid. It's considered as the Lewis acid because you know that it is having insufficient electrons. It is having only the 6 surrounding. It is having only the 6 electrons surrounding. But AlCl3 forms Al2Cl6. It forms Al2Cl6. That is, it is undergoing the dimerization, and that is possible only in the vapor phase, and in which it is not behaving as a Lewis acid. In that, it is not behaving as a Lewis acid. So you need to remember all of these points. Now I'm making the structure of the Al2Cl6. Now you have to remember the structure of this respective compound, that is the structure of the Al2Cl6. They will ask you that it is the dimer, is it present in the vapor phase, is it the Lewis acid? You have to answer whatever is written according to the data given to you. Now, this respective bond present on the above and the down is given the name as 3 center 4 electron bond. Now what do you understand by the 3 center? There is one aluminium, one chlorine, and then again one aluminium. 3 center, that means 3 atoms are present. Aluminium, chlorine, aluminium, aluminium, chlorine, and again aluminium. Okay. 4 electrons. 2 electrons are present over here. 2 electrons are present over here. Now how you are able to identify that? See, chlorine, whenever you will see the outermost electrons around the chlorine, these are present as 7. So it is only involving these 3 electrons in the bonding. One of the electron chlorine is using with the sharing with aluminium. Other 2 electrons it is donating to the aluminium. Similarly, this chlorine is sharing this electron with the aluminium, and these 2 electrons are donated to the aluminium. So 3 center, and how many number of electrons are present in this whole of the bond? 1, 2, 3, 4. 4 electrons are present. So 3 center 4 electron bond it is. Okay, you have to remember this is a 3 center 4 electron bond. This is not a Lewis acid. It is a dimer of AlCl3 and all these things. Okay. So this is a data based question and you have to remember. Now let's move forward to the next question. AlF3 is ionic, rest all of them are covalent. And if you want to know the reason for that, you can calculate this with the help of the Fajan's rule. We have discussed the Fajan's rule in the chemical bonding. Fajan's rule. You can simply say that for the ionic character, there should be bigger the size of cation, or there should be the smaller size of anion. Okay, you can follow this for the ionic character. So you know that in all of these aluminium is common, so we have to see the anion. Smaller the size of anion, greater is the ionic character. In all of these anion, fluorine is having the smallest size, so you can answer very easily. Now another question that can be asked to you from the halogens is the adduct formation. Another question that can be asked is the adduct formation. Now, when BF3 reacts with ammonia, what happens? BF3 is a electron deficient compound. Okay? It is an electron deficient compound, right? These two electrons, these two electrons, these two electrons. Okay? So how many electrons are surrounding? 6 electrons are surrounding the boron. Okay? Now what about ammonia? Ammonia is electron rich. Now what about ammonia? Ammonia is electron rich. Lone pair is present over here and there are 3 hydrogen atoms forming the bond. This is ammonia molecule. This is electron rich because it is having the lone pair. Now what this respective ammonia will do? It will donate this respective electron density to the boron. Because boron is only having 6 electrons around itself, it is behaving as the electron deficient molecule. It is behaving as the Lewis acid. है ना? It is electron deficient. Even you can write it as Lewis acid, and even you can write it as the Lewis base, Lewis acid or the Lewis base. This electron density is donated to the boron. Okay. Now, what you will see as a result? What you will see as a result? This electron density is donated to the BF3. Is donated to the BF3. So this bond you can have like this. This ammonia is forming the bond with the boron like this. This is a coordinate bond. This electron density is donated to the boron. This electron density is donated to the boron. This electron density is donated to the boron. Okay. These two electrons are shared also and donated also, because if some of you are not knowing about the dative bond, I must tell you that in the case of the dative bond, electrons are donated also and electrons are shared also. Nitrogen has not given completely these two electrons to boron. These two electrons are present equally between the nitrogen and the boron. They are donated also and they are shared also. Both of these things are occurring simultaneously. Okay. Now, everybody is happy now because electron deficiency is not present in the case of the boron now, and ammonia is also having the 8 electrons surrounding. Now how many electrons are present around boron? 1, 2, 3, 4, 5, 6, 7, 8. And in the case of the ammonia, electrons present are 1, 2, 3, 4, 5, 6 and again 7, 8. So these two electrons are the part of the boron also and the nitrogen also. Now remember the product. What is the product they are going to get? NH3 positive and BF3 negative. This is the result of the product they are going to get. This is the product they are going to get. Now always remember that earlier the hybridization of BF3, the boron hybridization is sp2. But after accepting the electron density, it becomes sp3, because you can simply answer from here also. How many sigma are there? 1 sigma, 2 sigma and 3 sigma. है ना? So how many sigma are there? There are 3 sigma. So hybridization over here will be sp2. And here how many sigma? 1 sigma, 2 sigma, 3 sigma and 4 sigma. 4 sigma will give you hybridization as sp3. So hybridization will increase. In the case of the nitrogen, there are 3 sigma plus 1 lone pair. So number is coming out to be 4. So it is sp3. And there also, how many sigma bonds are there? 1, 2, 3, 4. Here there are 4 sigma, so the hybridization will be sp3. So always remember the one which is the donor atom will have the increase in the hybridization during the formation of the dative bond. So in nutshell, we can write the acceptor atom. The acceptor atom has increase in the hybridization, by 1 unit, has increase in the hybridization by 1 unit. If it is sp2, it will become sp3. If it is sp3, it will become sp3d. Anything it can be. And I have explained you with the help of the sigma and every of the concept which is required in the chemical bonding. I have given so much time to this question because I have to explain you whatever is required, because now you are at the 11th standard. You should know everything. Okay. So hive. And yes, what is adduct? Adduct. This whole thing is called as adduct. Okay, this whole thing is called as adduct. Now let's move forward. Now moving towards the next, which is some important compounds of the boron family. What all important compounds we have to study in this respective chapter or the family, we can say. The first important compound we have over here is the borax, is known as the borax. The formula for the borax is Na2B4O7 dot 10H2O, or we can write Na2B4O5 OH4 dot 8H2O. These two important formulas we need to remember. Na2B4O7.10H2O, Na2B4O5OH4.8H2O. Now borax, also known as tincal. Common Indian name is Suhaga. So it can come as a one-word question. What is Suhaga? Na2B4O7.5H2O is known as the jeweler's boron, also named as the sodium tetraborate pentahydrate. Na2B4O7. Now this is .5H2O they are talking about. Borax is having the 10H2O. Okay. Na2B4O7 is known as the boron glass. So all these things you need to remember, which is related to the borax. Now we have to discuss about the preparation of the borax. So first it can be prepared from the columenite, which is a kind of ore we have. It is a kind of ore we have. Ca2B6O11. It reacts with the sodium carbonate to give you your respective anhydrous borax first. This is anhydrous borax. Now borax is a white crystalline solid and can be prepared by the boric acid also. Okay. When you react the boric acid with the sodium carbonate, again you are going to get the borax, which is anhydrous form. Obviously, when you will react this with water, you will get the .10H2O as the product. Okay. Now, if you undergo the hydration of this respective compound, if it will undergo the hydration, the product will be Na. The product will be Na2B4O7, Na2B4O7 dot 10H2O. Na2B4O7 dot 10H2O will be the product. Okay. Now, the structure Na2B4O7 dot 10H2O they can write, or Na2B2O2OH4 they can write. Okay. Now, I think they have written this formula as incorrect. This will be B4O5. Now, first understand how this respective formula you can learn easily with this whatever is written on the blackboard. Now 2 Na, so Na2 you can remember, 4 boron is present, 1 2 3 4, 4 boron is present, 1 2 3 4 5, 5 oxygen are present in between, so they are alone oxygens, so I can write it over here as O5, B4O5, OH4, 1 2 3 4, there are 4 OH, 1 2 3 4, 4 OH dot 8 H2O. I think I should write this formula myself, which is Na2 B4O5, Na2 B4O5, OH4 dot 8 H2O. This is the correct formula. Okay, just to have a remembrance of this only. Now, there are so many questions that can be asked from this. There are so many questions that can come from this. Now, how many bridged oxygen are there? How many bridged oxygen are there? So, 1, 2, 3, 4, 5. 5 bridged oxygen are there. How many BOB? How many BOB bonds are present? That is also 5. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. 5 BOB bonds are present. After that, how many BOH bonds are present? How many BOH bonds are present? 1, 2, 3, 4. 4 BOH bonds are present. After that, they will ask you how many boron are sp2 hybridized. So, this respective boron is having only 3 sigma bonds. Only 3 sigma bonds. Only 3 sigma bonds. 1 sigma, 2 sigma and 3 sigma. Whereas this has 1 sigma, 2 sigma, 3 sigma, 4 sigma. So there are 2 borons which are having hybridization as sp2, which is first one and the third one, which is the first one and the third one. And there are borons which are sp3 hybridized are also 2, which is 2 and 4. So sp2 hybridized boron will be 2 and sp3 hybridized boron will also be 2. One is here and other is here. Okay. Now the next thing they can ask you is, what is the N factor? Since this boron is having -2 charge, the N factor will be 2. One negative charge over here, one negative charge over here. Okay. So this whole of the ion is having the charge as -2 and the cationic charge is also +2. So either in the case of the salts you can take the positive charge or you can take the negative charge. Anything you can take. You will have your N factor as 2. So all these things are asked with respect to the borax. What is the formula? What are the properties related to the structure? This is something very, very important. Whenever I will write something very, very important, I will have the 3 stars. This is very, very important. After this, we have over here, borax bead test. We have over here borax bead test. Now, in this case, you have your borax Na2 B4O7 dot 10 H2O, Na2 B4O7 dot 10 H2O. We apply the heat, it becomes anhydrous. Na2B4O7, it becomes anhydrous. First, it becomes anhydrous by losing the 10 molecules of the water. After that, again you heat it. You are going to get sodium borate. plus boric anhydride. Sodium borate plus boric anhydride. This is borate of sodium, or you can simply say sodium borate, and this is your boric anhydride. This is your boric anhydride. This is your boric anhydride. Okay? I hope you have understood. Now, this respective part as a whole looks like a glassy bead. This whole looks like a glassy bead. Now, what do you understand by the glassy bead? You people somewhere in your lifetime have taken some tablets, which is omega-3 tablets. You know omega-3 tablets. Same, you just pick up one of the tablet of from the bottle, and that will have same appearance as this. You can consider that, you can imagine that respective one tablet contains sodium borate and the boric anhydride. But obviously it contains something else, but appearance of the glassy bead is similar to that. It is similar to that. Okay. Now, this respective glassy bead, this glassy bead, this respective glassy bead is used in the analysis as preliminary test. Preliminary test in salt analysis. We have salt analysis in which we have some salt. So if we perform the glassy bead, borax bead test, with the help of the color, we can identify which of the metal is present or which of the cation is present. Okay. So what you do, you take the metal, you react the glassy bead, with it, and you are going to get the metal meta borate. You are going to get the metal meta borate, which is having the formula like this. Metal meta borate. Now, colors: cobalt, copper, chromium, titanium, nickel, and the manganese. You have to remember the color. Whenever you react these beads with the metal, you will have some of the color. These have the blue color. Chromium is having the green color, not the same as what is written on the blackboard. Titanium is having the yellow color. Manganese is having the pink color, whereas nickel is having the brown color. So with the help of this metal meta borate, this metal meta borate will have some color, and you will be able to identify the cation. Okay. Obviously, because this is what? This is M plus 2 and BO2 negative. Okay. Now this M plus 2 is a cation. We have the cationic part in our salt. We have the anionic part in our salt. So this glassy bead test can help you to identify the cation present in the salt. Okay. So this is the borax bead test, and this is very, very important. This is beta very, very important. Borax bead test. Okay. Now let's move forward towards the next compound, which is your orthoboric acid, which is H3BO3, orthoboric acid. Now there are so many things related to the orthoboric acid. It is a white, soft, needle-like crystals having a soapy touch. Everything I'm underlining is very, very important. It is white, needle-like crystals it is having, and it is having the soapy touch. After that, they will tell you something about the N factor, but that I will explain you. And this is the structure. This is the structure of the boric acid. You can simply see the structure of boric acid over here. This is your boric acid, or you can simply say H3BO3. Boric acid, you can simply say H3BO3. Now, what is the N factor of boric acid? N factor of boric acid is 1. Now, some of you might think that for the case of the acids, the N factor is decided by what? Basicity. That is how many ionizable H positive ions are present. है ना? It is decided by the basicity. But in the case of the boric acid, that is not the case. The N factor will not be decided by the basicity. Okay. So how it is decided? What happens when this boric acid is dissolved with the water? It reacts with the water. It starts reacting with the water. Okay. And it forms a compound which is BOH4 negative. Okay. Along with that, there will be release of the 1H positive ion. And this 1H positive ion is responsible for the N factor. This 1H positive ion is responsible for the N factor. This is responsible for what? The N factor. See, N factor for an acid is decided by how many H positive ion it can release in the solution. Okay. Like for the H2SO4, it is 2H positive ion, HCl it is 1, because that is decided by the basicity, that is the number of ionizable H positive ions present. But here I am not writing like, this is not the case that I am writing H3BO3 and I am writing H2BO3 negative and then I am writing H positive. I am not writing anything like this. It is not a protonic acid. Okay, now let me explain you one thing. There is a difference between protonic acid and the monobasic acid. Okay. Now, one of the word is protonic acid. Now, what do you understand by the word protonic acid? There is a word which is protonic acid. H3BO3. H3BO3 is a protonic acid or it is a monobasic acid. Now there is a question in front of you. Now protonic acid is someone which dissociates itself to give H positive ion. It will dissociate itself to give H positive ion. But in the case of the monobasic acid, always one H positive ion, it will provide in the solution. Okay. Protonic acid is someone who will always dissociate itself and then only it will give. For example, if I say I have H2SO4, it will dissociate to give you HSO4 negative and then H positive ion. So you will say that in the present case the N factor is 1. You can dissociate one more also, you will get the N factor as 2. But I cannot say, this is not possible that H3BO3 dissociates to give you H2BO3 negative and H positive ion. This is something not possible. This is incorrect. So always and always remember that H3BO3 is a monobasic acid. It can never be the protonic acid. Okay. It's true that in the solution, this H3BO3, in the solution, this H3BO3, when it is reacting with water, it is forming BOH4 negative and there is a release of 1H positive ion. Okay, there is a release of 1H positive ion by any of the means, but it is not releasing by the dissociation of the H3BO3. So, This is a question from the mole concept. This question is asked from the mole concept. So I have explained you. This can be asked in the mole concept chapter, that what is the N factor of H3BO3. So always remember this. This whole I have explained you. Everything is written on the blackboard. So I will read once, that it does not give 3 H positive ion but accepts one lone pair of electron from water. So N factor is 1. This is a monobasic Lewis acid, as oxygen gives one electron pair to the boron, so it acquires positive charge and becomes unstable, so it furnishes one H positive ion and gets stable. Now they are explaining you with the help of the mechanism also. Now you know that boron is having 2 electrons over here, 2 over here, 2 over here. Right now it is behaving as electron deficient. So what happens? Water is simply donating its lone pair of electron to the boron. It is donating the lone pair of electron to the boron. So what is happening as a case? What is happening as a case is this. H positive, this whole compound. Okay. This water as a result will have, I should write one more step also in between, so you will understand in a more better way. This BOH whole thrice. Okay. Now there will be a bond between oxygen and this HOH, and there is a bond between BOH whole thrice, and oxygen is having the positive charge. Now this H positive will be removed. This H positive will be removed, and as a result you are going to get, HO BOH whole thrice plus 1 H positive. Okay. Whole of the mechanism also I have explained. If you have any of the doubt, everything should be clear to you, because this is a basic. They can ask you anything, because in the 11th standard, in the school or wherever you are studying, they can ask you anything. They will not ask you only the MCQs. They will not ask you only the one line statement question. Subjective questions can also come in the 11th standard. So you should know the every reason behind what is happening. Okay. Okay. Now, next thing. Whenever you break the boric acid, you're going to get a compound which is HbO2. It is called as meta boric acid. It is called as metaboric acid. Okay. Now, if you break metaboric acid, if you heat metaboric acid, you are going to get the tetraboric acid. Or if you heat this respective orthoboric acid to this respective temperature, you're going to get the tetraboric acid. After that, you are going to get the boric anhydride. If you further heat, you are going to get the boric anhydride or boron trioxide or boron sesquioxide. Whenever there are 3 oxygen atoms, we somewhere write sesquioxide. Okay. So remember, first orthoboric acid is heated to give you metaboric acid. After that you get the tetraboric acid, and after that you get the boric anhydride. This is a series of the reactions undergoing, and this is the structure of the boric acid. This is the structure of the boric acid. Now, one boron, other boron, this is the other boron, and this is other boron. Now I am making the hydrogen bonds. Now I am making the hydrogen bonds over here, so that you can easily able to identify, this is the structure of the boric acid. Okay. This is a sheet like structure. This is a sheet like structure. This is a sheet like structure, है ना? And that sheet is due to the hydrogen bonding. Due to the presence of the hydrogen bonding, it is having the sheet-like structure. So you have to remember every of the point present in the boric acid. Let's move forward. Now, moving towards the next part. Now we have a very important compound present at the next, which is the boron hydride, boric hydride. And it is asked, I think, almost, I don't know, infinite times the question has come from this respective compound. Now, moving towards the next. Orthoboric acid we have completed. One more thing I want to add on this is, because of this, it is also used as a lubricant. It is also used as a lubricant, okay? And even you can write the uses also. You can also write the uses also for this respective compound. The uses are, it is used as the food preservative. It is used as a food preservative, and even if you want to have the preparation also, even we can have the preparation also of this respective compound. I will write the preparation over here. I will write the preparation over here as a flow chart so that it will be easier for you to remember. This is your H3BO3, okay? So what you can do is you can take your hydride of a boron, even you can take a borax and react these both with water. React these both with water. Here you are going to get the product as your respective H3BO3 plus hydrogen, and here you are going to get NaOH plus H3BO3. Okay? Always remember the solution of borax is basic. Solution of borax is basic because when we are undergoing the hydrolysis of this, we are going to get the strong base. We are going to get the strong base. This question has come in the JEE mains this year only, that what is the aqueous solution of Na2B4O7, that is basic. Okay, so these are the important things which are used in the preparation of the orthoboric acid. Anything else we need to add on over here is, no, we have done almost everything. Okay, now moving towards the next part, which is hydrides of the boron, which is the hydrides of the boron. Okay, so we should have a topic, the hydrides of the boron. Now, first of all, when we are talking about the hydrides of the boron, we need to understand some of the important things. Hydrides of boron. See, there are so many hydrides of boron, but here we have to study only one, which is the B2H6. Which is the B2H6, the hydrides of the boron, which is the B2H6. Now, there are so many important things attached to this respective compound. It is very, very important. First of all, we have to discuss the preparation. First of all, we have to discuss the preparation. First of all, we have to discuss the preparation of this compound. This can be prepared first of all with the help of the lithium aluminium hydride, because it is used as the reducing agent. Even you can react the sodium borohydride with I2. This is also a reducing agent. And sodium hydride with the BF3. All of these reactions can produce the hydride of the boron. So lithium aluminium hydride will reduce the boron trifluoride to give you first the B2H6, which is the product of this reaction due to the presence of the reducing agent, lithium aluminium hydride. Okay, after that, one is lithium fluoride and other is aluminium fluoride as the product. So one of the desired product you have got with this respective reaction. Here you are going to get first of all your desired product B2H6, and this will reduce I2 into NaI. From this 0 it is undergoing -1 as reduction with the release of the hydrogen gas. So this reaction will also give you the desired product as B2H6, and here also you are going to get your respective B2H6 and sodium fluoride. B2H6 and sodium fluoride. So these all reactions are used simply in the preparation of the B2H6, and you need to remember all of them. After that, now we have to understand the structure of this respective compound. Structure of this respective compound, that how the structure of this respective compound is made. This is very, very important. Very, very important. Boron family itself is very, very important. So many questions are coming from this family. Now understand. We have BH3 with us. When we undergo the dimerization of BH3, that is the dimer of BH3, we get the B2H6. The dimer of BH3, we get the B2H6. Okay. Now, what is happening? This is still a Lewis acid. You need to remember this is still a Lewis acid. Now, boron is having electronic configuration as 1s2, 2s2, 2p1. And if we excite, we get 1s2, 2s1, 2p2. If we excite, we are going to get this. Okay. Now, if I make the box structure, it is like this. Now, since you can see, this boron is electron deficient, that's why it is called as Lewis acid. That's why it is called as Lewis acid. Okay, perfect. Now, what happens is, when we make the structure of this respective compound, there is one boron present over here and it is surrounded by 3 electrons. Okay. One, there is hydrogen atom, other hydrogen atom, and there is other hydrogen atom. Okay. These are the electrons of the hydrogen, and they are simply forming the bond between them. They are simply forming the bond between them. No problem, bond is formed. After that, we have one electron of the hydrogen also. Okay. Now let's make another boron. It is having its electron over here, and over here. Now there are some other hydrogens also. One hydrogen over here, one hydrogen over here, and one hydrogen over here. So let's draw the electrons of the hydrogen also. So these are the electrons of the hydrogen. Let's make the bond also. One bond over here, one bond over here. Normally I have made the bonds. Normally. Okay. Now these bonds are called as 2 center, 2 electron bond. What it is called as? 2 center, 2 electron bond. 2 center, that means 2 atoms. One is boron, one is hydrogen, 2 center. And how many electrons are present in this bond? 2 electrons. So 2 center, 2 electron bond is present. This is also 2 center, 2 electron bond. This is also 2 center, 2 electron bond. This is also 2 center 2 electron bond. So I'm writing over here, there are 4 2 center 2 electron bonds, right? I can write over here there are 4 2 center 2 electron bonds, and these are called as the terminal hydrogens. Terminal hydrogens, because 1, 2, 3, 4 all are called as the terminal hydrogens. If you want, I can make a circle on this so that you will be easily able to identify them. Okay, you will be easily able to identify them. Boron is making bond with the hydrogen, and these are the terminal hydrogens. When they are connecting themselves with the boron, they are forming the 2 center 2 electron bonds. Now this boron is combining with this above hydrogen like this, and this boron is combining with this hydrogen like this, right? I hope you people can see. This bond is called as 3 center 2 electron bond. This bond is called as 3 center 2 electron bond. How many center? 1, 2, 3. 3 atoms. So that means 3 center. 2 electron bond. 1 electron is of the boron, other electron is of the hydrogen. 2 electron bond. 3 center 2 electron bond it is present over here. Okay. So how many 3 center 2 electron bonds are present? 3 center 2 electron bond present, 2. One is above and one is below. Whole of this bond is called as the 3 center 2 electron bond. How many 3 center 2 electron bonds are present? 2. One is above and other is below. Okay. These bonds are also called as the banana bonds. These bonds are also called as the banana bonds. As you can see, the shape is all related with banana. Banana is somehow twisted like this. So there is one banana above, there is other banana down. One banana above, other banana down. So these are also called as the banana bonds. These are also called as the banana bonds. Okay. I'm writing everything which is present over here. Now let's discuss some of the important points. It's a 3 center 2 electron bonding called banana bonding. It's a 3 center 2 electron bonding which is also called as the banana bonding, or even you can call it as the bridge bonding, because you know that they are present as the bridge. They are present as the bridge. Even you can call them as the bridge bond also. Okay. Now next point. Number of bonds. For all of these things, you have to refer to the structure like this. Now terminal hydrogens. Now terminal hydrogens are the one which are present with the pink one. This is called as the terminal hydrogens, and the one which is the bridging hydrogens I am making with the yellow color. These are the bridging hydrogens. Okay. You have to remember all of these things very, very nicely. Now there are some of the bond lengths written over here. There are some of the bond angles written over here. See, this respective angle which is present because of the banana bonds is 97 degree. This bond angle is larger, this bond angle is smaller. Why? Because they are not connected to something else after this. They can expand their bond. They can expand their bond. They cannot expand because they are connected here also. This boron is connected there also. So they are having a limitation that they cannot expand themselves very much. Okay. So you have to remember the bond angles first. This is without the banana bond. This is with the banana bond. Okay. Bond length. This bond length is smaller. This bond length is larger. Whenever you have a smaller bond length, your bond is stronger. Whenever you have a larger bond length, your bond is weaker. You can simply write over here, these banana bonds have larger bond length. These banana bonds are having the larger bond length. That's why they are weak bonds. That's why they are the weak bonds. And if I make the total number of sigma bonds over here, 1 sigma, 2 sigma, 3 sigma, 4 sigma. So I called boron as the sp3 hybridized. Now you will ask me, ma'am, that how it is sp3 hybridized with the help of the orbital picture you have made. For the orbital picture you have made, now understand. In the case of the boron, we have 2s over here, 2p over here. All of these orbitals participate, they all participate in hybridization. They all participate in the hybridization. So hybridization over here will be sp3. Hybridization over here will be sp3. And even you have to write one more point over here, that empty orbitals also participate, can also be involved in hybridization, can also be involved in hybridization. The empty orbitals can also be involved in the hybridization. So you have to remember everything which is present over here and this whole data. Okay, now some of the questions over here. Number of bonds of the bond length 119 picometer, which is of the terminal bonds, terminal bonds. So it is 4. You can simply see 1, 2, 3, 4. 4 bonds have bond length as 109 picometer, and number of bonds of the bond length 134 picometer. 1, 2, 3, 4, which is the bridge bonds. Number of bonds having the bond angle as 97 degree. 1, 2, 2. So only 2 are present. This is also because of the banana bond. And bond angle as 120 degrees, again 2. 1 and 2. This is because of the terminal bonds. Number of atoms present in the same plane. Now, this you have to understand that when we are making this structure, all of these atoms are in the plane, whereas one is above the plane and this hydrogen is below the plane. Okay, this is above, this is below, and all these 6 atoms are present in the plane. I will draw the diagram like this. Okay, I will draw the diagram like this. This is whole plane is present over here, and one atom is present above and one atom is present down. Okay, one atom is present above and other atom is present down. This is present above the plane. This is present above the plane, whereas this is present below the plane. One is present above the plane, whereas other is present below the plane. Okay, I hope this is clear to everyone. Next we have the structure. Now, the reactions of the reactions of diborane. This structure is called as the diborane structure. Diborane. Now, B2H6. Now, this B2H6, which is the diborane, it gives so many reactions. It reacts with excess of the ammonia. It is going to get a compound which is known as BNX, which is known as boron nitride. It is known as boron nitride. Now, it reacts with water to give you boric acid along with the hydrogen gas. You are going to get the boric acid along with the hydrogen gas. After that, if you undergo the oxidation of this, again you are going to get the boric acid. Even the oxidation will also give you the boric acid. Then you have two ammonia molecules but with the low temperature, and you have two ammonia with the high temperature, low temperature and the high temperature. This is called as B2H6.2 ammonia. This is called as B3N3H6. This is called as B3N3H6. B3N3H6, which is also called as borazine, which is also called as borazine or inorganic benzene. It is also called as inorganic benzene, or borazine or inorganic benzene is the name of this compound. This compound is called as boron nitride, or you can simply say inorganic graphite. This is also called as inorganic graphite. Boron nitride is also called as inorganic graphite. Now we are going to make the structures of all of these compounds. So, so we have the infinite sheets of the boron nitride similar to the graphite. There is a sheet of the carbon-carbon bonds in the case of the graphite. Then again there is a sheet of the carbon-carbon bond, and there is the van der Waals forces present. We will discuss the structure of the graphite in the carbon family itself, but I think you people have studied in the class 10 chapter also. It is having this kind of structure only. And the borazine, and if I donate the lone pair of electrons to boron, we are going to get this respective compound. This is the structure of B3N3H6. Now you can simply see this is exactly similar to the benzene. Just replace all the boron and nitrogen with the carbon, carbon-carbon double single bond, and attached with that is the hydrogen. So C6H6, B3N3H6. Inorganic benzene, borazine, all of these reactions are present for the diborane. Now, let's see the structure. If you want to see, in the case of the bookish language, this is the structure of the diborane, which is B2H6. So, these bonds are called as the banana bonds. Okay. See, this is something very, very important. So, that's why I have given you the every picture possible. This is also banana bond and this is also banana bond. Okay. Rest is the terminal hydrogens. So, we are done with the diborane. We have discussed every of the important point of the diborane. Now, some of the questions we have. Boric acid is polymeric due to, boric acid is polymeric, you know, H3BO3. There is a two-dimensional sheet-like structure we have. But why it is possible? I have explained you this. This is the structure of the boric acid. There is a sheet-like structure which is possible due to hydrogen bonding. So that is possible due to the hydrogen bonding. Okay. Next we have, which of the following element has exceptionally high melting point? I have told you that boron has B12 existence. It is a very giant network covalent solid. It is a giant network covalent solid. It is a giant network covalent solid. I must tell you that gallium has the lowest melting point. It can melt on the palm. If you keep the gallium on your palm, it will start melting. Okay? As you remember the order, this is the order of the melting point of this respective family. Okay, beta? Next we have, which of the following compounds banana bond is present? Only one, which is B2H6, we have discussed right now. Boron compounds which behaves as a Lewis acids because of their, always whenever anybody is behaving as a Lewis acid, the definition of Lewis acid is electron deficient character or the nature. Okay, this is a very easy question. Which type of hydride is a BH3? They are Lewis acids. They are electron deficient hydrides. They are Lewis acids. They are Lewis acids. After that we have, which of the following statement is correct regarding the B2H6? Each boron is sp3 hybridized. Yes, I have made this. I can show you over here the structure of the diborane. I can show you the structure of the diborane. I have explained you that boron over here is sp3 hybridized. I have explained you the structure of the diborane. And from there you can easily identify that what kind of a hybridization it is having. So this is correct. B2H is electron deficient. I have already written that it is a Lewis acid. It is having a banana bond, and all of these statements are correct. Okay. Now let's move towards the next part. Now we have to start the next family, which is the carbon family. As you know that the p block elements consist of the groups which is 13 to 18, and in the class 11th we have to study group number 13 and group number 14. Group number 13 we have discussed all of the important points. Now we have to start discussing the group number 14. So whenever you are starting any of the group, first you have to go through the elements present in that respective group, and the elements present in this respective groups are carbon, silicon, germanium, tin, lead, flerovium. All these elements are present in the group number 14. So first of all, you should know the names of all these elements: carbon, silicon, germanium, tin and lead. This respective element flerovium is not that much important with respect to the studies, with respect to the physical properties or the chemical properties, because it is very newly discovered, right? So obviously many of the properties we still are not knowing, we are discovering, we are going through the facts related to this respective element. So only you should know the atomic number of this respective element, and that is also very easy for you to remember, that this is the group number 14, so it will have 114 as the atomic number, so easily you can remember. Okay, and the electronic configuration, see, if you want to know the electronic configuration of this respective group, the general electronic configuration, I am writing over here, the general electronic configuration will be ns2 np2. Always the general electronic configuration will be ns2 np2 for this group. Okay, so in all of the elements you can see the order which is followed in all of these elements, which is 2s2 2p2, then we have 3s2 3p2, then we have 4s2 4p2, then 5s2 5p2, 6s2 6p2, 7s2 7p2, 7s2 7p2. In all of these elements you can simply see that the electrons are filled in the s as s2 and p as p2, right? You can write the electronic configuration in the form of the noble gases, that is helium, neon, argon, krypton, xenon, radon. First you can write the noble gases that you are remembering. Okay, after that you can write the simple electronic configuration, because you know that carbon is present in the period number 2. So you will have 2s2 2p2, then silicon is present in the period number 3. So 3 respectively 4 5 6 7 represents the period number, right? Okay, now the atomic numbers. For the atomic numbers, you have to remember the magic numbers. With the help of the magic numbers, you can easily remember the names, easily remember the atomic numbers of all of the elements. Okay, so first is your, just remember the carbon one. Carbon is 6. Almost everybody is knowing the atomic number of carbon, so it will be very easier for you to start. Okay, after that, add 8 over here. So when you add 8 and 6, you are going to get 14. After that, you have to add 18 over here. So 8 plus 4 is 12, and then you're going to get 32 as the atomic number. Then add 32 plus 18. 8 plus 2 is 10, and 3 plus 1 4, and 1 5. So 50 will be the atomic number. Then add over here 32. So 2 plus 0 is 8 plus 5. You're going to get 32. Okay. And then again add 32. And you are going to get your atomic number as 114. Okay, 82 plus 2, that is 4, 8 plus 3 is 11, and you're going to get the 114 as your atomic number. All these numbers, you know that these are magic numbers, and that I have explained you in the chapter. Which is periodicity. So these all are the magic numbers. Okay, all these are your magic numbers. I have written J, it should be G, because I was writing majority magic numbers. Okay, after that you should know atomic radii values are not required to be learned. They are not required to be learned. Just you can see from the value of the atomic radii, if you will see, you will get to know that if the values is written over here, I will explain you this over here only. Atomic radii. Atomic radii, if they are going to ask you, just remember one thing. When you are moving from top to bottom, your shell's number increases. That's why your size also increases, right? So you can simply see second shell, third shell, fourth shell, fifth shell, sixth shell, seventh shell. You go on down and you will see that there will be increase in the number of shells. So obviously the size will increase, and you can see that with the help of the values also. It's something very easy. We know that when we are moving from top to bottom, sizes increase because of the increase in the number of shells. I'm just writing for you, but you people already know this. Okay, so you have to remember only this respective box. Everything else you know. Right? So atomic radii we have done, atomic number we have done, we know the element's name. This is a synthetic element. This is a synthetic element. Synthetic element is the one which is man-made. This is synthetic element. And even you should know the nature of all these elements, right? You should know the nature. Only one mistake over here. This is not a metalloid. This is a non-metal. Silicon is a non-metal. It's not a metalloid. Everything else you know. Yes, germanium is metalloid, carbon is non-metal, rest all of them are metals. So everything present on this respective sheet is something you should know when you're starting to study a group. What are the elements present? What is the electronic configuration? What is the atomic number? And what is the nature? Are they metal or they non-metal? Because after that you will be able to understand its properties in a more different way, in a more easier way. So first always remember the electronic configurations, right? So first only property I have written over here, which is atomic radii, because I'm having the values over here. So you can see the values also. It's not required to learn. Don't learn these values. Nobody is going to ask you the values, guys. Nobody. Don't learn. Don't learn the values. Don't learn the values. Not required. Nobody is going to ask you the value of what is the radii of the carbon in the mathematical value. They are simply going to ask you the trend, that what is happening when you're moving from top to bottom. That when you're moving from top to bottom, your size will increase. Okay, because that there will be increase in the number of shells. After that, now we are going to start the physical properties, in which we have already discussed the atomic radii. Now we are going to discuss the electronegativity. And you can see from the values of electronegativity, carbon is highly electronegative in this respective group. As you can see also that carbon is having a very small size, and the smaller size you have, greater electronegative you are. Okay. So we can say that the order of the electronegativity is highest is the carbon, then we have the lead, and then this silicon is nearly equal to germanium, and that is nearly equal to tin. So this is the order you have to follow. You don't need to remember the electronegativity. You don't need to remember the values. Nobody is going to ask you the values, but you need to remember the trend. Trend is important, okay? Trend is very important, and you should know. So what all elements in this respective group have almost similar electronegativity values? Yes, this question can come. Which is having the highest value? This question can come. Okay. So I think the most important point over here is that three elements which have almost equal electronegativity, this question or this point is very important for you. Right? Let's move forward. After that, we need to discuss the next property, which is your ionization enthalpy. Which is your ionization enthalpy. Which is your ionization enthalpy. Now you people know it very well that what is the definition of ionization enthalpy? That is energy required to remove most loosely bound electron, outermost electron, whatever you want to write, to remove outermost electron, from an isolated gaseous atom. from an isolated gaseous atom. Energy required to remove outermost electron from an isolated gaseous atom. This is the definition of the ionization enthalpy. Now you know that ionization enthalpy is inversely proportional to the size. If you have a greater size, you will have a very less ionization enthalpy, because very less amount of energy will be required to remove the outermost electron. Okay, and one other factor on which it depends is your ionization enthalpy is directly proportional to the Z effective. Is directly proportional to the Z effective, which is effective nuclear charge. Now, how you will understand this? This most of the people can relate with the size, but whenever I write the Z effective, you people get into the confusion. Now, I will explain this. Now, what happens? This is your nucleus and this is your outermost electron, right? There is outermost shell and there is one electron present in this respective outermost shell. Okay. Now, there are some shells present inside also, and there are some electrons present inside also. Okay. This is the charge which should be applied on this respective outermost electron. The charge of the nucleus which should be applied on this outermost electron. Okay, and there are some electrons present inside. So what is happening? That these pink electrons, the shells, the inner shells in which these pink electrons are present, they are actually creating a shield in between, that the charge of the nucleus is not completely on the outermost electron. Okay, if this is the nucleus, this is the outermost shell. Okay, so charge should go like this, but there is a shield present in between, so charge is, it's not able to move. Now this charge is not able to move. Okay, so this respective outermost electron is not able to get the complete charge of the nucleus, is not able to get the complete charge of the nucleus. So these respective inner electrons are shielding the outermost electron from the nucleus. The inner electrons, the electrons present in between, are shielding the electron, the outermost electron, from the nucleus, that the outermost electron cannot easily get the charge of the nucleus. Okay, this is shielding effect. I have explained you many times: periodicity, chemical bonding, and S block, now P block. So many times I am repeating the same thing. Okay, now what is happening? Now what is happening? There is an equation. You know that there is an equation. I'm again explaining, but you know that there is an equation. I have explained in the periodicity chapter itself. This equation I have explained in the periodicity chapter itself. Now what is Z effective? Z effective is the actual charge which is experienced by the outermost electron. Now because of these inner electrons, it is not getting the complete charge of the nucleus. Let's say if I remove all of these pink electrons from inside, will there any repulsion? No, this nucleus will completely give its charge to the electron which is the red colored electron, the outermost electron. There will be no shielding, there will be nothing. Easily the charge of the nucleus will go to the outermost electron. Okay, that will be the complete charge of the nucleus which is given to the outermost electron. But due to the presence of these inner electrons, due to the repulsive interactions, now you will see that you will think that, ma'am, what is repulsive interaction? Now what is happening, beta? If I draw the green color, this green color is the attraction of the nucleus to the outermost electron. But if I want to draw the repulsive interaction, there are some repulsions also, है ना? There are some repulsions also. These repulsions I have made with the help of the blue color. These are creating a shield. These repulsive interactions are creating a shield so that the nucleus is not able to give the charge to the outermost electron. The left charge which is experienced by the outermost electron, whatever left charge is experienced by the outermost electron, is the Z effective. Whatever charge the outermost electron is getting, 1%, 2%, whatever percent the charge is experienced by the outermost electron, is the Z effective. What is Z? Z is the actual charge, what the outermost electron should experience if all of the electrons I removed from inside. Let's say if I remove all of these pink electrons from inside, and this nucleus will give its rays to the outermost electron. Whatever the charge is experienced by this outermost electron, the full charge, the actual charge which it should get is the Z. And what is sigma? Sigma is the repulsive forces, the shielding constant, whatever shielding is created, whatever shielding is created, I put that all shielding into this term, which is sigma. Obviously this can be calculated with the help of the Slatter's rule, but right now we are not required to know all these things. I will take a class for the Slatter's rule, but that is only the value that you will get as a number, but the concept will remain the same. All the shielding effects, all the shielding constant, all the repulsive interactions, I just put into the sigma term. Okay, so Z effective is the charge which is experienced by the outermost electron, considering all the shielding values, considering all the repulsive interactions. What is Z? Z is the actual charge which outermost electron should experience. Okay, sigma is the repulsive interactions, the shielding which is present between the nucleus and the outermost electron. Whatever the pink part, whatever is the repulsive interactions, I will put that into the sigma. Okay, obviously if I subtract the full charge, there is some full charge. What is a full charge? If I take this nucleus, if I take this outermost electron, this is the full charge. I'm not taking anything in between. I'm not taking anything in between. I'm not taking anything in between. I'm simply saying that the outermost electron, what charge this outermost electron should experience, that is the Z. But you know that there are some shells present inside, there are some shells present inside in which there are some electrons present. Okay, that's why the charge of the nucleus cannot completely go to the outermost electron. Now there will be some left charge which will be experienced by this outermost electron, will be called as Z effective. And due to all these values, you are getting Z effective. Okay, and all these values are put under the term sigma. So this is the rough explanation of what is happening in the shielding effect. This is the rough explanation of what is happening in the shielding effect. I have already explained you all these things in the periodicity chapter. I have just made you a very quick revision so that you can relate with me in a more better way. Okay, so Z effective equal to Z minus sigma is the equation. What is Z effective? Actual charge experienced by outermost electron. And what is Z? And Z is and this is shielding constant. So you should know the value of everything. What is Z effective, what is Z, and what is sigma. Okay. Now, I am telling you that your ionization energy is directly proportional to the Z effective. Now, why that when the Z effective increases, ionization energy also increases? Let's say this is my nucleus, this is my outermost shell, and this is the electron present in the outermost shell. Okay, there are some shells present inside, and in which there are electrons also present. Okay, so this is the charge which is experienced by the outermost electron of the nucleus. If this charge is increased by any factor, let's say Z effective is increased by any factor, nucleus is able to apply its attractive forces more to the outermost electron. If this is the outermost electron, this is a nucleus, and this is your Z effective, the charge experienced by the outermost electron of the nucleus. So if this charge, this attraction increases, if this Z effective, this attraction increases, so what happens? this respective electrons removal will become hard. If Z effective increases, this respective nucleus can attract this outermost shell very effectively, very closely. So the removal of this electron will become hard. So ionization energy will increase. These all things are important to understand because you people should know all these things. Because so many times this word is used, Z effective, sigma, Z, so many times these words are used, and every time whenever these words are coming, we need to at least go through them again so that you can relate with what is explained in the periodicity chapter. Okay, or maybe structure of atom. Actually this is explained in the structure of atom chapter. Okay, periodicity has the, because in the structure of atom you study about the attractive forces, you study about the repulsive forces when you study the multi-electron system. In that you actually get to know the shielding effect. Okay, perfect. Now the order. So when you think carbon, silicon, germanium, tin, lead, so when you are moving from top to bottom, your size increases, so your ionization enthalpy should decrease. So the order of the ionization enthalpy will be highest for the carbon, then silicon, then germanium, then lead, and then tin. Now some of you will ask me, ma'am, that I think you have written an incorrect order because you have changed the lead and the tin. Ma'am, why you have done this? Please explain us. Ma'am, why you have done this? Please explain us. Now, answer is in the electronic configuration. Flerovium, just don't discuss anything about flerovium. But in the case of the lead, you can see in the case of the lead, you have F electrons also and you have D electrons also. I think there is one zero missing over here. 5d10. Okay, there are d electrons also, there are f electrons also, so that there is a poor shielding effect. I'm writing this as 10. I think this is not written. 4d10. Okay, so you can simply see over here that in the case of the lead, there is a poor shielding effect. There is a poor shielding effect of D and F electrons, as the electronic configuration is xenon. 5d10, not 5d10, we have to write 4f14, 5d10, 6s2, 6p2. So it has F and D, both electrons which have the poor shielding effect. That's why its Z effective will increase. That's why in the case of the lead, the Z effective will increase, ionization energy will increase. See, I have not written that there is a change in the size, but yes, there will be the change in the ionization enthalpy. Whenever there is Z effective increase, the nucleus will attract the outermost electron in a more tighter way, more effectively, so that the removal of the outermost electron becomes difficult. Okay, I think you people have understood all of the things related to the ionization enthalpy I have written. Just remember the exception over here, which is of the lead and the tin. Okay, now let's move forward. Ionization enthalpy, we are done with this. Now we have the density. Now talking about the density, the order is, when we are moving from carbon, silicon, germanium, tin and lead, when you are moving from top to bottom, your density increases. Okay, because your mass increases. Okay, so the order should be carbon, silicon, germanium, tin and then lead. But there is some exception in this order also, that silicon is over here and carbon is over here, order of the density will be like this. Now I'm writing in the place of the silicon a circle with the help of the two stars, that this is an exception, that silicon is having the lowest density, and you need to remember it very, very nicely. Obviously, mass increases top to bottom, your density will also increase, normal order, but silicon will have the lowest density, and this is something exceptional order. Please remember it. After that, we have melting point and the boiling point. Talking about the melting point. Moving from top to bottom. Moving from the top to bottom. Okay. Now what is happening? If you talk about the boiling point, there is a normal order, which is carbon, silicon, germanium, tin, lead. The order will be followed like this. When you're moving from top to bottom, your respective boiling point will decrease. Same we think about this also. Carbon, silicon, germanium, tin, lead. But yes, there is again an exception with the case of the lead and the tin. Lead will come first and tin will come first. Tin will come afterwards. Again, there is an exception. Whenever I am writing an exception, I will always write 2 stars. Now what happens in the lead? That lead is having a greater melting point as compared to tin. This is the reason. Same reason. Attraction of the outermost electron is more. There are tight forces, there are stronger forces, more energy will be required to melt the element, to melt the metal, and you will see the exceptional order. Okay, so reason is here, as nobody is going to ask you the reason, but yes, trend can be asked, and you need to remember the trend very, very nicely. Okay, so let's move forward. After that, we have catenation. Now you know that catenation is the favorite property of the carbon. So catenation is something we have to understand also, and this is most important for this family, because the element which is doing the highest catenation in whole of the periodic table is coming under this group itself. Okay, so we have the elements carbon, silicon, germanium, tin, and lead. We have all of these elements. So what you normally see is catenation. First, what is catenation? Catenation in one word is defined as self-linkage. Like if I'm carbon, again I have a very similar to me a person which is also will be called as carbon, this carbon, and we have a bond with each other. Like you in the in your childhood, you people have played a game which is called as chain, है ना? So what is happening? So many people are forming chains with each other. Obviously, you people were not all same. You all have different faces, different appearance, but you all are human being. So carbon, you can relate with the human being, and you form chains, and you were playing the chain game. Since I have played, so I think you people have also played. Games are almost same only in your childhood also, in my childhood also. Okay, so it's simply called as the self linkage. In one word, you can define it as like this. In one word, you can define it like this. Okay, now what is happening? Carbon is having the highest catenation. Carbon is having the highest catenation. Carbon is having the highest catenation. Okay, and lead do not undergo catenation. Do not undergo catenation. Do not undergo catenation. Okay. Now the order. Carbon very, very high, silicon, and then we have germanium nearly equal to tin. Lead do not undergo catenation. Lead does not undergo catenation. Now what is the problem with the lead? Why lead is not undergoing catenation? Because you know that when two small atoms are forming the bond with each other, the bond will be stronger. But if two bigger atoms are forming the bond with each other, I should make the correct picture. I should make the exact picture. What is happening? If you make the smaller atoms bond, okay, this will be the bond. If you make a bigger atom bond, bond length, this is the bond length in this case, this is the bond length in this case. If I define the bond strength of this bond A and B, so you will see that when you're moving from top to bottom, bond strength decreases. This is a stronger bond, this is a very weaker bond. Very small amount of energy if I give to this bond, it will break. So if you are making the catenation of this respective bigger atom, how it will survive? Because the bonds present are very, very weak. If you will apply very small amount of energy, they will break. So you have to understand the fact. I'm not deleting this. You can have a idea at what is happening. I'm not deleting this, okay? I'm writing over here. Bond length increases and bond strength decreases. So if there will be no strength in the bond, so how you will be able to go catenation? Like we were playing the chain game. Okay, we have, when the chain becomes very bigger, we all are running towards one direction. So we have to form a very strong grip, because if the grip is not strong, the chain can break, right? People used to play the game. We had, because when the chain was moving in particular one direction, we all had that grip, the strong grip. That is the, the mode of the survival of that chain. And same is the concept here also. Bond length increases, bond strength decreases. If I form the bond of the lead and so many lead, the bond is very weak. They are not able to make that self linkages. Okay, so catenation is not possible for lead, but all other elements will undergo the catenation. Okay, now let's move forward towards the oxidation states. Now let us move towards the next topic, which is oxidation states, which is the oxidation states. So whenever we are talking about the oxidation state, we need to know the general electronic configuration, which is Ns2Np2, which is Ns2Np2. Now, electronic configuration is having 2 electrons in the s orbitals and the 2 electrons in the p orbitals. So what I can do is I can take any of the m element, and if I make the excited state of that element, I am going to get how many unpaired electrons? I am going to get 4 unpaired electrons. I'm going to get 4 unpaired electrons. That means I can have my oxidation state as +2 and I can have my oxidation state as +4. Two types of oxidation states are possible for this respective group. Now, again, carbon, silicon, germanium, tin, lead. All of these elements we have. If I talk about the stability of the oxidation state, so the order will be similar to what I have explained you earlier in the group number 13. Similarly, for the above elements, higher oxidation state is stable, but for the lead, the lower oxidation state is stable. Now, if you want to know the reason we can write due to inert pair effect. Due to inert pair affect lower oxidation state, lower oxidation state, lower oxidation state is more stable for the last element, is more stable, is more stable for the last element, is more stable for the last element. So you have to remember that for the lead, +2 oxidation state is more stable. That's why we have over here some of the points related that are PbO2 is less stable than PbO. The reason is same, the oxidation state. For the lead, higher oxidation state is not stable, lower oxidation state is stable. That whole of the part I have explained you in the boron family in the inert pair effect. Okay, but if I ask you another question, let's say I'm not writing this over here, I'm making a new page. Now, there are so many things we need to understand on this concept. First of all, they will ask you that the stability of lead O2 and lead oxide. So, you will simply say, yes, ma'am, this is stable. Okay. Now, they can ask you one more thing, that lead F4 exist, but lead I4 do not exist. Why so? That lead F4 exists, but lead I4 do not exist. Now, understand one very important thing. That is, what happens when lead I4 do not exist? What happens? It will dissociate. It will dissociate to give you PbI2 plus I2. It will dissociate to give you PbI2 plus I2. Now, why it is happening? Let's see. The oxidation state of lead +4 is changing into the oxidation state as lead +2. So, lead is getting reduced and it is getting stabilized also. Lead is happy because lead is very unstable in the +4 oxidation state. If this will dissociate in this form, lead will be very, very happy. What about iodine? Iodine here is having oxidation state as -1, whereas here it is having 0. So I should explain you this also, that iodine in the -1 oxidation state is less stable than iodine in the 0 oxidation state. Okay, this also you should know, because this is the order for the halogen family, the order of the reducing agent, that iodine is the best reducing agent, then bromide, then chloride, and then fluoride. Now, what do you understand by this respective trend? Iodine is the best reducing agent, iodide ion. Okay, it's a very good reducing agent. It will reduce lead +4 into lead +2. It behaves as a very strong reducing agent. So, as a result, it will oxidize -1 into 0 itself. If it is reducing someone, it is oxidizing itself, reducing agent. So, in a product side, both of them are happy. Lead is also happy, getting from +4 to +2, happy. And iodide ion from -1 to 0 is also happy. So, this respective reaction is changing its form from lead I4 to lead I2 plus I2, because in the product side they are more stable. Okay, lead PbI4 are just forming a bond because of some endothermic reaction. You have just mixed lead and then iodine, and you have formed lead I4 by giving some energy, but whenever you will stop supplying that energy, they will break to give you this respective compound. This reaction is also called as intramolecular redox. You have studied this in the redox chapter, that this reaction is called as intramolecular redox when one of the compound is getting oxidized also and reduced also. So you should remember that iodide ion in whole of the halogen family is the best reducing agent, and I've written over here also this, and you know that due to the inert pair effect, the oxidation state lead plus 4 is less stable than lead I2. Inert pair effect, we know all these things, okay? But why then PbF4 exists? Why? Let's say if I dissociate PbF4, let's say if I try to dissociate PbF4, let's say, then it will form PbF2 and F2, PbF2 and F2. Now, lead is moving from plus 4 to plus 2. Okay, lead is getting reduced and lead is getting stabilized also. No problem. Lead is getting reduced and lead is getting stabilized also. But what about the fluoride ion? Fluoride ion is moving from -1 to the 0 oxidation state, and this F negative ion is the very poor, is the poor, very poor reducing agent. It cannot reduce any other element respectively, because it is the poorest reducing agent. So my dear students, this respective reaction cannot take place, because fluoride ion will say to lead, see lead, you are getting reduced, you are getting happy, you are not stable in the plus 4 oxidation state, I understand. But what about me? I'm not stable in the 0 oxidation state, I'm stable in the -1 oxidation state. I want to behave, I want to remain as -1 only. I don't want to become 0. So this reaction cannot occur, because here both are satisfied, lead and iodide both, because in the product side both are happy. Here F negative is not happy, है ना? It is not a very good reducing agent. It will not behave as a reducing agent either. So beta, I think you people have understood that why PbF4 exists, whereas lead I4 do not exist and dissociate. It does not exist and it dissociates, right? I think you people have understood. Now we have one more concept related to this inert pair effect. I think we are done. This is something very important question, and you have learned so new things in this respective topic, intramolecular redox, about the reducing agents, which is a better reducing agent, which is not a better reducing agent, all of these things. So please remember it very nicely, okay? Even I'm writing over here that, see, this question is coming so many times, that PbO2 is less stable than PbO and SnO2 is more stable than SnO. I think reason you people are knowing, plus 4 plus 2 plus 4 plus 2. Reason is in the inert pair effect. Reason is in the inert pair effect itself. For the 10 plus 4 oxidation state is more stable, so that's why I have given this sign, okay? This question is important because it is coming in the examination, so that's why I have written, okay? Now, oxidation state we are done. Now the next part, we have to move now towards halides. The compound of the halogen family with the carbon family. Halides. First, remember that whenever you are forming the halides, any of the M element you take with this family and react with halogen, you are going to get MX2 or you are going to get MX4. These two types of compounds are possible, as you know that the oxidation states possible is +2 or the +4, okay? But remember that M can never be the carbon. So I'm writing over here, carbon do not form halides directly. Carbon cannot form the halides directly. Carbon cannot form the halides directly. If you want to prepare the halide of the carbon, just take methane, react with Cl2 gas. In the presence of light, you are going to get CH3Cl plus HCl. And further, if you react again with the Cl2, you are again going to get CH2Cl2. This reaction we have done in the class 10th standard. So they cannot form halides directly. You have to use some indirect method for the preparation of the carbon halides, and this is written on the blackboard. Okay, perfect. Now, what are the halides possible? In the +2 oxidation state, we can have carbon, silicon, germanium, tin, and lead. And here we have carbon, silicon, germanium, tin, and lead. So first of all, we have all of these compounds present with us. Okay. First of all, we have all of these compounds present with us in the +2 oxidation state and in the +4 oxidation state. Now, when you're moving in the +2 oxidation state, when you're moving from top to bottom, stability of +2 oxidation state increases due to IPE, which is inert pair effect. Stability of +2 oxidation state increases due to the inert pair effect. So when you're moving from top to bottom, stability increases. I will write the order. I think I should write the order, that will be more beneficial for you. Okay. When you're moving from top to bottom, your stability of +2 oxidation state increases. Stability increases. Whereas in the case of all these compounds, when you're moving from top to bottom, they will have their stability decreases, because when you're moving from top to bottom, lower oxidation state stability increases due to IPE, which is inert pair effect. And when you're moving from top to bottom, higher oxidation state stability decreases, that is also due to inert pair effect. That is also due to inert pair effect. So always remember these two things, that what is happening for the +2 oxidation state, +4 oxidation state. In the case of the +2 oxidation state, stability top to bottom increases, because when you are moving from top to bottom, due to inert pair effect, stability of lower oxidation state increases, higher oxidation state decreases, and same goes for the halogens also. Same goes for the halogens also. Right. Now, moving towards some next points. Sometimes they ask you that why CF62 negative does not exist but SiF62 negative exists. If I ask the existence of this compound, this does not exist, but this compound can exist. How it is possible? Now, first I talk about the carbon. Carbon. Electronic configuration 1s2, 2s2, 2p2. This is the electronic configuration of the carbon. And if I make the excited state carbon, 1s2, 2s1, 2p2. 1s2, 2s1, 2p2. 1s2, 2s1, 2p2. Okay. 2p3 we will have, not 2p1, 2p2, 2p3 we will have. So how many number of unpaired electrons you have? You have 4 unpaired electrons. That means your covalency can be 4. That means you can form only the 4 bonds. If you have 4 covalency, that means you can form the 4 bond only. What about silicon? Silicon is having electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p2. So when I make the excited state silicon, I will have 3s2, 3s1, 2p, 3s1, 3p, 3. And here I have 4s0 and 3d0. Okay. So this is silicon having 1 electron. This is p orbital having 3 electrons, and there is a presence of empty d orbitals also. This is your 3s, this is your 3p, and this is your 3d. So by using all of these 4 respective unpaired electron, it can form first SiF4. And using the 2 orbitals of the 3d also, it can form SiF6 2 negative. By using these 2 d orbitals, it can form SiF6 2 negative. Now how you are forming the SiF6 2 negative? By forming the coordinate bond. That is a very deeper meaning that is not required over here, but yes, you can understand that using these 2 orbitals, it is forming the SiF6 2 negative. That means it can increase its covalency beyond 4. It can increase its covalency. It can increase its covalency beyond 4. It can form bond using the d orbitals, 3d orbitals. It can increase its covalency beyond 4. But what about the carbon? Do you have any, like I'm writing over here the 2s, I'm writing over here the 2p. Are you having any 2d? Are you having any 2d? This is not possible. There is no such kind of orbital existing in the nature. 2d never exists. So carbon cannot increase its covalency beyond 4, whereas silicon can increase its covalency beyond 4. This is the reason. So I'm writing over here, the reason I have explained you that carbon can increase its covalency, beyond carbon. Silicon can increase its covalency beyond 4, whereas carbon can not. Silicon can increase its covalency beyond 4, but carbon cannot. Why? Because carbon do not have empty d orbitals. Because carbon do not have empty d orbitals, but silicon has. You can see from the 3D. So this is something very, very important to understand, that your carbon with the covalent compound having 6 fluoride ions around it is not possible, whereas silicon having 6 fluoride ions around it is possible. For it can use these electrons to form SiF4, and along with that, if you want SiF6 2 negative, it can use the 2 orbitals of the 3D to form SiF6 2 negative, but that is not possible with the case of the carbon, right? Similarly, one more question is coming from this same topic itself, that is, why carbon Cl4 cannot hydrolyze, whereas SiCl4 can be hydrolyzed. Why CCl4 cannot be hydrolyzed but SiCl4 can be hydrolyzed? Why? Now the reason. First of all, I want to explain you the hydrolysis of the SiCl4. Hydrolysis of SiCl4. Understand this very nicely. Whenever you do the hydrolysis, you react with the water. Water is H positive and OH negative. H positive and OH negative. So, hydrolysis of SiCl4, first we need to discuss. Whenever we talk about the hydrolysis, okay, so silicon is having +4 oxidation state over here and Cl is having -1. So whenever there is a hydrolysis, the positive part goes to the negative part and the negative part goes to the positive part. Normal. So what should be the product? It should be SiOH4 plus HCl. SiOH4 plus HCl. SiOH4 plus HCl. This should be the product. But how it is taking place, how this hydrolysis is happening, that we need to understand. First, if you want to write the reaction, you can simply write the reaction looking over here. But how it is happening? Now, this is the structure of SiCl4. Whenever you are reacting with the water, you are actually reacting with the OH negative. You are actually reacting with the OH negative. So this OH negative will come and attack the silicon. Why? Why? Silicon is electropositive, whereas chlorine is electronegative. I think you people have done the hydrocarbons chapter. You know that whenever there is a negatively charged species, it is electron rich. It is electron rich. It moves towards someone which is electron deficient. So hydroxide will move towards the silicon. Okay. For this respective step to occur, there should be presence of empty orbital. There should be the presence of empty orbital. Okay. Silicon. If I talk about silicon, I have already explained you here only. Like SiF4, the bond was SiCl4 in the present case, SiCl4 hydrolysis. So SiCl4, all the orbitals are used in the bonding. All these 4 orbitals are used in the bonding. Now you have empty d orbitals present with the silicon. The hydroxide is coming and attacking the silicon. Hydroxide is having a negative charge. One negative charge means it is having a lone pair of electron. One negative charge is equal to a pair of electron. One negative charge is equal to the pair of electron. Whenever it is moving towards silicon, it will donate its lone pair of electron into the empty orbital of the silicon. That is the empty 3d orbital. Empty orbital we need 3d, 4d, whatever it has. Empty orbital it should have. There is a presence of the 3d empty orbital. Okay. Done. So it has empty 3d orbital. So this step can occur. So whenever you are attacking the silicon with the hydroxide, there will be one chlorine removed as a result. So one chlorine will be removed as a result. Okay. Now what will be the product? Si OH, Cl, Cl, Cl plus HCl, because you know that this H positive is not involved in the bonding, and Cl negative, when it is removed, it will attach with the H positive and you will get this as your product. You will get this as your product. Now again you react this with water, another Cl will be replaced, again another, all the Cl will be replaced and you will get SiOH4 plus 4HCl plus 4HCl, that you will get. But the major condition for this attack, the major condition, the necessary condition required for this respective step to occur is the presence of the empty d orbitals. Okay, presence of the empty d orbitals. Now what about the carbon? Why I'm writing that CCl4, the carbon cannot hydrolyze? Because in the case of the carbon, you are forming you are using all of these orbitals and you are forming CCl4. Now next, you are not having any orbitals. So how hydroxide ion will donate its pair of electron? Where it will donate the pair of electron? You are not having any orbital. So hydroxide cannot attack. Hydroxide cannot attack. So the hydrolysis will not occur. CCl4 cannot hydrolyze. Just one line answer you need to write. I have explained you, but you only have to write only one thing, that carbon does not have empty d orbitals. Carbon does not have empty d orbitals. That's it. Answer is completed. Carbon does not have empty d orbitals because the first step involves the presence of empty orbital and it was not having. Okay, so you need to understand, you need to remember that CCl4 cannot be hydrolyzed, whereas SiCl4 can be hydrolyzed. I hope this is clear to everyone. It's a very, very important question. It's a very, very important question. Okay, perfect. Now another question which can come: why PbF4 and SnF4 are considered as ionic? Why they are considered as ionic compounds? Now let's say I have CF4, SiF4, GeF4, then we have SnF4, and then we have PbF4. So when you are moving from top to bottom, your ionic character increases. And these two are considered as the ionic compounds, because for the ionic character is directly proportional to the size of cation and inversely proportional to the size of anion. Just use this respective formula and you are going to get the answer. Size of cation directly proportional, which is the largest size of the cation, tin and the lead, so they will be ionic. This is the answer. Okay, simply you have to answer on this respective basis. I hope this is clear to everyone. Now the next series of compounds we need to study for this respective family is the oxides. Oxides of this family. So they form two types of oxides, that is CO, silicon oxide, germanium oxide, and tin oxide and the lead oxide. Then we have CO2, SiO2, germanium oxide, SnO2, and then PbO2. So we need to know the nature of these. Carbon monoxide is considered as neutral. Tin oxide, lead oxide is considered as amphoteric, is considered as amphoteric oxides, is considered as amphoteric oxides, the lead and the tin, whereas rest all of them are the acidic oxides, because rest all of them are amphoteric. Rest all of them are amphoteric, not amphoteric, acidic, because rest all of them are non-metal and non-metal forms. So acidic oxides, okay? Acidic oxides, rest all of them. Just remember neutral. What are the neutral oxides we have? We have water as the neutral oxide, carbon monoxide, N2O and NO. All these are neutral oxides. All these are neutral oxides. Okay, so you can easily learn all these things. And the stability of the +2 oxidation state and +4 oxidation state of the oxides I have already explained you in the inert pair effect. Okay, okay, just move towards the next part. Let's move towards the next part. Now moving towards the important compounds of the carbon. I should not say the compounds, it is an allotrope of the carbon. Graphite, diamond and the Buckminster fullerenes. You know these all compounds, but now you have to learn some more properties of these allotropes. Carbon has 3 types of allotropes: graphite, diamond and fullerene. What is allotrope? They might have some different appearance. Okay, they might have some different properties, but they are made of the same constituent element, which is the carbon. Okay, so first we have to discuss about the graphite. First we need to discuss about the graphite. So coming towards the graphite, each carbon is sp2 hybridized. This is the structure of the graphite. Now, how many bonds a graphite can form? This is a carbon atom, this is a carbon and this is a carbon. So one graphite carbon is forming 3 bonds. So 1 sigma, 2 sigma, 3 sigma. The hybridization of each carbon will be sp2. Hybridization will be sp2. Hybridization will be sp2. So I'm writing over here, it is sp2 hybridized. It has layered structure. It has the layered structure. Yes, this is a layer. It has a layered structure. This is a layer. Then again we have a layer. Then again we have a layer. So you have a layer type structure. After that, whatever important points are there, I'm just making them circled. Layered structure. These layers are attracted by van der Waals forces. These layers are attracted by van der Waals forces. Yes, there will be some forces present over here. Yes, there will be some forces present over here. There will be some forces present over here. These forces are weak van der Waals forces. These forces are weak van der Waals forces. These forces are weak van der Waals forces. And that too we have studied in the states of matter chapter. Okay. These layers are attracted by the van der Waals forces. This is also important. This is also asked. So I am making it underline also. Each carbon has 1 free electron in the p orbital. So it is a good conductor. Now what does it mean? Now what does this mean? Since carbon is forming only 3 bonds, you know that the electronic configuration of carbon is 1s2, 2s2, 2p2, and if I make the excited state carbon, it is 1s2, 2s1 and 2p3. 1s2, 2s1 and 2p3. So, 1 orbital of the s and 3 orbital of the p. So if it is forming only 3 bonds, so only 1, 2, 3. 3 electrons are used in the bonding. This is not involved in the bonding. This is not involved in the bonding. This is not involved in the bonding. So this respective electron is delocalized. It is moving from here, there, anywhere on this respective layer, and that unpaired electron, that alone electron, is responsible for its good conductor of electricity nature. All electrons get delocalized in one layer and form pi bond. Graphite is aromatic. Graphite is aromatic. I don't know if you people are knowing right now the aromatic or not, but since you have done the GOC, there we study about the aromatic compound. So graphite is aromatic. Electron jumps from one orbital to another, hence is a good conductor of heat and electricity. There is one unpaired electron which is responsible for it being the good conductor of the heat also. Okay, electricity is also there and heat is also there. We can write over here, it's a good conductor of heat and electricity. Graphite, carbon-carbon bond length is 141 picometer. Carbon-carbon bond length is 141.5 picometer, and distance between the two layers is 340 picometer. That you can see from the structure itself, the carbon-carbon bond length, and this is 340 picometer. This is 340 picometer. The carbon-carbon bond length is 141.5, whereas the layers have the distance, which is adjacent layer has a distance of 340 picometer. Okay. Graphite is used as a lubricant. Graphite is used as a lubricant. Even you should remember that it is a better lubricant. It is a better lubricant as compared to the oil and the grease. When you see the oil and the grease as a lubricant, they are not a good lubricant at a very high temperature. Why? Because they get denatured. They get denatured. They have some proteins present in them that have amino acids linkages that breaks, it gets denatured, but that is not present in the case of the graphite. So you can simply say that it is a better lubricant as compared to the oil and grease because it is working at the high temperatures also. So we prefer graphite over oil and grease. Okay, so graphite is used as a lubricant at high temperature. Oil gets burned or denatured at high temperature, but graphite does not get denatured even at high temperature, so preferred over oil and grease. So preferred over oil and grease. Okay, now let's move forward. This is the structure of the graphite. Now graphite marks the paper black. That's why it is also called as the black lead or plumbago, and so it is used in the pencil lead. We all know that we use pencil that is made up of the graphite. Composition of pencil lead is graphite plus clay. Sometimes you have heard that the pencils you used is a lead pencil, है ना? You think that the pencil we are using are the lead pencils, so it might contain some lead. So you should know that the percentage of the lead in the lead pencils are actually 0%. Lead pencils does not contain any lead. They contain graphite plus clay. There is no percentage of the lead present in the lead pencils. Okay. Graphite has a high melting point, so it is employed in the manufacture of the crucible. Crucible are simply the pots. They are the pots in which we melt some of the things which require very high temperature. There are some things which have a very high melting points. So if you will put them in some of the bowl that can melt very easily, so how you will reach to the melting point of the substance which is present inside? So whatever container you are making, you are having, in which you have put that respective substance, that crucible, that respective pot should have a very high heat resistance. It should have a very high melting point. So that's why graphite is used as a substance which is used in the making of the crucible. Okay. Crucible is something, just a pot. It is a pot in which you melt substances which are very high, which are having very high melting points. Graphite, when heated with the oxidizing agents like alkaline KMnO4, it forms mellitic acid. Now, whatever is written on the blackboard is important with respect to the JEE and advance. NEET or your school examinations are not going to ask you all these things. This is only for the JEE mains and advance, that whenever it is heated with the oxidizing agents like KMnO4, it is forming an acid which is present over here, which is also called as mellitic acid or benzene hexacarboxylic acid, because you are having the 6 carboxylic acids group, so you will write it as hexacarboxylic acids. Moving towards the another allotrope of the carbon, which is your diamond. Everybody loves diamonds. Diamonds are women's best friends, right? It's just one liners I'm using. I have also heard this from my childhood. It is the purest form of carbon. First of all, it is the purest form of carbon. Diamond is the purest. See, this question also comes in the examination, which is the purest form of carbon. So whatever is required, I'm underlining, and please refer that. It is the hardest natural substance known. Nothing is harder than diamond, which is natural made. Man-made things can be different. We are just talking about the natural things which we have found around us as it is. Okay. It is transparent. Yes, we know it is transparent and has a specific gravity of 3.52, and its refractive index is high, which is 2.45. These are some properties which you need to remember. Now 1 carat diamond is equal to 200 milligram, and diamond powder, if consumed, is fatal and causes death in the minutes. You should not consume diamond in any of the form. If you, by chance, this is the result. Okay. It is difficult to break. It is difficult to break due to extended covalent bonding. It is very difficult to break because it has the extended covalent bonding. Diamond is used. Why? Now you can see from here also. This is the structure of the diamond. This is one carbon atom. You know that a carbon atom can form 4 bonds because it is having 4 as its unpaired electron. So 1 sigma, 2 sigma, 3 sigma, 4 sigma, it is sp3 hybridized. Carbon is sp3 hybridized. And you can see from here that there is an extensive linkage. One carbon, then other carbon. Every carbon is attached to the other carbon, and that is a very big network of the covalent bonding. It is difficult to break due to extended covalent bonding. Okay. After that, diamond is used for making cutters. Cutters, you know, it can behave as a very sharp cutting substance, so it can be used as a cutter. Blades of diamond are used in the eye surgery. Okay. Eye surgical instruments has diamond. Okay. And as abrasive for sharpening the hard tools, because it is very sharp itself, it can be used for the sharpening of the hard tools. Impure diamond, which is the black one, are used in the knives for cutting the glass. These all are the uses of the diamond. It is the purest form, refractive index, specific gravity, its use, its numerical value in the terms of the milligram. These all are the learning things, not required for the board purpose, not required for the NEET purpose also. It is more important with respect to the JEE mains and advanced. They can ask all these questions, okay? After that, in diamond, each carbon is joined to the other 4 carbon tetrahedrally. I have already drawn the structure, and carbon-carbon bond length is 1.54 angstrom, and bond angle is 109.28 minutes, because you know that this is tetrahedral and tetrahedral has the same angle, 109 degree 28 minutes, having sp3 hybridization on each carbon. All 4 carbons, all 4 electrons in the carbons are involved in the bonding. Hence, it is bad conductor of heat and electricity. It is bad conductor of heat and electricity. Right? It's a very bad conductor of heat and electricity. This is all about the diamond we need to understand. Now let's move forward. The another isotope of the carbon, which is your fullerene, Now fullerene looks like this. The structure of fullerene. Fullerene is also a allotrope of carbon. It's a kind of allotrope of carbon which can contain carbon from 60, 70 and even above than that. It is a giant molecule which can have so many carbon atoms attached in it. See, 60 carbon atoms are making self linkages, a catenation property, to form a this much bigger molecule, fullerene. Buckminster fullerenes we call it as, but fullerene is also fine. Now, if you see the fullerene structure, you will see so many shapes. First, we have a pentagonal ring. In front, you have a pentagonal ring attached with you. After that, I'm making over here the rings attached to it. So hexagonal ring are after that. Then again we have a hexagonal ring. Then again we have a hexagonal ring. So we can simply say that this pentagon is surrounded by hexagon rings. This pentagon is surrounded by the hexagon rings. You can see from here that the hexagon is surrounded by the pentagon rings. You need to remember this. I'm not drawing this in a no purpose manner. Always a question can come that does pentagonal rings are surrounded by the hexagonal rings, or the hexagonal ring is surrounded by the pentagonal ring? So remember, there is one pentagonal ring in between surrounded by the hexagonal rings. There is no contact between one pentagonal ring and the other pentagonal ring. There is no contact between them. Okay, always remember. This is a point, important point. It was made as a result of action of a laser beam of strong heating of a sample of graphite in the presence of the inert atmosphere. It's just a preparation of fullerene, that how fullerene can be prepared. It's a sooty material containing carbon 60 with small amount of the carbon 17. You will get as a result, when you are going to do this respective above reaction, you are going to get a material, the sooty material, which will contain carbon 60 along with the carbon 70. Most common fullerene is C60, which is also called as the Buckminster fullerenes, which has football, saucer ball like structure. It contains 20 hexagonal, 6-membered ring and 12 pentagonal 5-membered ring. There are so many rings attached to it. You can see that there are some pentagonal rings, there are some hexagonal rings. So there are 20 hexagonal rings and there are 12 pentagonal rings present in the fullerene. Every ring structure is aromatic. Every ring structure is aromatic. Now, since you have studied the aromatic in the GOC, I don't need to explain. You should have a planar structure, delocalized electrons, and there should be every carbon every carbon sp2 hybridized. You should follow the Huckel rule, 4n plus 2 pi electrons. These are the things which you need to follow for the aromatic compounds, and you people have done that. It is used to make the ball bearings also. Ball bearings are simply a substance which is used to decrease the friction. It is like a circle in which some points are present. It's just a material which is used to decrease friction, and there are some other uses also. You can simply just remember it is used to make the ball bearings. So these all were the allotropes of the carbon: graphite, diamond, and the fullerene. Now we need to discuss the some important compounds of the silicons also. So let's move towards the important compounds of the silicon. The compounds of the silicon we have compounds of silicon. Compounds of silicon we have, first we have the silicons itself. First we have the silicons itself. First we have the silicons itself. Now what are the silicons? First of all, these are the organo silicon compounds. These are the organo silicon compounds in which silicon is attached with the alkyl group and the chlorine. Okay, this linkage is present, organosilicon compounds along with the chlorine. Okay, because of the alkyl group, because of R group, they are water repellent. Because of the alkyl group, they are water repellent. They are bad conductors. They don't have any kind of conductivity. They are bad conductors, and even they are inert also. All these things are first the classification of the silicons. Now, how many types of silicons you have? Like you can have R3 SiCl, you can have R2 SiCl2, you can have R SiCl3. All these types of silicon and R and the chloride containing compounds are present. First we have 3R groups, then 2R groups, and then 1R group. So whenever you're going to make the silicon from this respective part, you are going to get the cross-linked polymer. How? I will explain you. You're going to get the cross-linked polymer. With the help of the R2Cl2, you are going to get the linear polymer. And with the help of the RSiCl3, you are going to get a dimer. And the question is always coming from this respective part, and this is only the important part in this respective topic. Now, first we should discuss about the dimer. First we should discuss about the dimer formation. Now, what happens exactly is you have R3 SiCl. We react this with water. So you have H positive and OH negative. You react this OH negative to the silicon, and as a result you are going to get the product as R3SiOH. As I have already explained you in the hydrolysis, Cl is removing, OH negative is entering into the molecule of the 4 bonds containing silicon. Right. After that, what we should do is we should take these two type of molecules, R, Si, R and R, and this is OH. And then again we should take the same molecule. This is R, this is R, and this is R. So water is removed and we are going to get this as the product. R, Si, R and R, O, and the 3R are present along with it. So this is the product you're going to get as a result. Now it's a dimer. After that, linear polymer. There will be chain, 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 chain. There will be a linear polymer. Now how you're going to get a linear polymer? That you need to understand. Let's make first R2Si Cl2 reacts with H positive and OH negative. It reacts with water. R2SiCl2, it reacts with water. You are going to get R2SiOH whole twice. Now we are going to get the linear polymer. We take the n number of molecules of this. First I am going to react only the two groups. This is silicon, this is R, this is R, this is OH, and then we are going to take the another molecule which is OH, Si, this is R, and this is OH. Product you are going to get is this OH, Si, this is R, this is R, this is Si, this is R, this is OH. Now, if you are reacting only the two molecules, you are going to get this respective product. But if I take n number of molecules of this respective molecule, so another molecule I will attach over here. There will be water removed, so this side chain will increase, right? So this side the chain will increase. And similarly, if I attach this side, this chain will increase. So I can simply write over here, if I do the polymerization of n number of molecules, polymerization of n number of molecules, I am going to get the product as Si, this is R, this is R, this is R. So this is the product you are going to get. Okay. It's a linear polymer. If you are taking the n molecules, it will go to the n number of whatever molecules you have taken, and if you are taking only the two, so it will be like this. That you have a possibility to increase the chain from this side also and this side also. But in the case of the dimer, you cannot increase the chain from any of the side anymore. So we are limited to the dimer only. After that, we have in the third part, we have the cross-linked. In the third part, we have the cross-linked. Now, what do you understand by the cross-linked? We have R, SiCl3. We react this with water. We are going to get RSiOH whole thrice as our product. Now, this is R, Si in between, this is OH, and this is OH. Now, you can form your respective cross-linked polymer from any of the sides. So you are going to get the polymer like this. You can increase the chain from any of the sides. This is a cross-linked polymer, RSiCl3. You can increase the chain from this side, or from this side by reacting with the other molecules. Okay, so this is called as the cross-linked polymer because you have more number of sites which can react with the other molecule. Cross-linked, one, if you're having only this side, this is linear. If you're having along with the linear one other more site, that will be called as the cross-linked polymer, right? Even you can have the dimer of it, which is SiRO, silicon R, oxygen, and then like this. So you can have this kind of a set of the cross-linked polymer also, in which you have attached four groups like this to form a cyclic structure. Just for your knowledge, I have made this structure. If you can have more silicon atoms, you can make the more also. Now we are moving towards the next class of the compounds, which are silicates. Now we are moving towards the next class of the compounds, which are called as the silicates. Now silicates are the compounds which are formed from SiOH4. If you react again that with the base, you are going to get SiO4, 4 negative. Iron. This is also written as H4 SiO4. You are going to get a ion, a polyatomic ion. This is called as the silicate. SiO4, 4 negative, having the structure like this. Having the structure like this. This is tetrahedral. The structure is tetrahedral, as you can see, having the hybridization as sp3. Now what you have to do in this silicates is something you need to understand. I am making the structure of the silicates in some different manner and you have to refer that. Let's say this structure is like this, and there is one silicon present in between, and there is one silicon present in between. Okay, and these are the negative charges, and these are the negative charges. Now, how you have to relate this with this? See how this structure is present. Silicon is there, one oxygen is above. This is silicon, one oxygen is above, and three oxygens are present down. So the above oxygen is this one. And below the oxygen, there is one silicon atom, which is represented by the red color dot. And below silicon, there are again three oxygen atoms present, which is 1, 2, and 3. I am looking from the above. The silicon is, I am looking like this. This is silicon, and beyond silicon, there is 3 oxygen atoms. And there is above 1 oxygen atom. So you have to assume this structure like this. Okay. So please first follow what ma'am is saying. This is your oxygen and this is your silicon. Oxygen and the silicon. Now, there are so many types of silicates we have to study. That is orthosilicates, pyro, cyclic, chain. So many we have, right? So let's start first of all with the orthosilicates. The basic unit is called as the orthosilicate. The very basic unit is called as the orthosilicate, which is SiO4, 4 minus, which can be made like this. Simple, that we have made now itself. Okay. There is no oxygen atoms shared anywhere. There is no oxygen atoms shared anywhere. It's a simply one unit, orthosilicates. Okay. These do not share any corner. These do not share any corner. The anions are discrete, that is single SiO4 4 negative units. Example is zircon. Zircon. Now how it is made? Zirconium is having valency as +4. SiO4 is having the charge as -4. Multiply it and you are going to get the zircon. Similarly for a stride you can get magnesium having the charge +2 and SiO4 is having the charge -4. Make it a cross multiply and get your answer. Okay. Now we have the pyrosilicates. In the case of the pyrosilicates, in the case of the pyrosilicates, in the case of the pyrosilicates, the unit is Si2O7 6 negative. There is one oxygen atom shared. There is one oxygen atom shared. Now how it is present? If you will see, the structure is going to be represented like this. One oxygen atom is shared, and if I make the other type of a structure, it will be like this. It will be like this. One silicon in between, one silicon in between, and the charges you are going to get over here is 6 negative charge, which you can simply refer from this structure. So this oxygen is shared. This oxygen is shared. Shared oxygen. Right? Can refer both of the structure. This is the shared oxygen in the pyrosilicates. Okay. They can ask you that what is the charge and what number of oxygen atoms are shared. Okay. So you need to remember. It's written over here also. They share one corner to form this respective unit and they are also called as the island structure. The example is thottwetite. This is also very easy. Scandium is having oxidation state as +3 and Si2O7 is having as -6. So multiply these two and get your answer. So multiply these two and get your answer. Now after that, we have with us, now after that, we have with us third point, which is the chain silicates. Now the third point is the chain silicates. In the case of the chain silicates, the unit will be SiO3 -2 and N. The unit will be SiO3 -2 N. Okay. There will be 2 oxygen atom shared. Now making the structure. You can also make the structure with me. So with respect to one silicate unit, 2 oxygen atoms are shared. Okay, with respect to one silicate unit, 2 oxygen atoms are shared, and this is the basic unit. If I'm using the 3 silicon atoms, I'm having like this. I can have what number of rings? I can have silicon atoms as 3, 4, 5. That depends upon the what bigger chain you want. Okay, so this is your chain silicates. Okay, now referring to the written here, 2 corners of each tetrahedral, that means 2 oxygen atoms are shared. And to form the closed ring, the anionic unit is called as SiO3 2 minus. Okay. Example, wollastonite, which is the calcium containing compound. Okay, if they are having 3 silicon atoms, so you will write over here Si3, the oxygen 9, so 6 negative charge will be there. 6 negative charge will be there, and you can see the 6 negative charge 1, 2, 3, 4, 5, 6. Okay, now how you're forming this respective compound? Calcium is having +2 as the charge, and Si3O9 is having the -6 as the charge. Make it a cross multiplication and get your answer. Same goes with the help of the beryl also. In the case of the beryl, they are having Si6. So you will have silicon N as 6, 6 3s are 18, and 6 2s are 12 as -12 charged. Okay, beryllium is having charge as +2. So 3 beryllium, 3 + 2, and aluminium is having the charge as +3, but there are 2 aluminium. So 3 2s are 6 and 3 2s are 6. There will be total +12 charge, and there will be -12 charge. Okay, so units, you can, if you are able to identify the units, you can easily answer the question. Okay, perfect. After that, after the chain silicates, even we have the, I have written here the chain silicates, it should be cyclic. It should be the cyclic silicates. And beta, always remember that in the case of the chain silicates also, in the case of the chain silicates also, in the case of the chain silicates also, you have to follow the same. Unit will be same, SiO3 -2 N, and yes, 2 oxygen atoms are shared, and it will look like this. One silicon in between, and the negative charge will be like this. So for per silicon containing unit, there will be 2 oxygen atoms shared. So the oxygen atoms shared will be also same, and there will be the unit, basic unit will also be same. Okay, so please remember this very nicely. What are the chain silicates? What are the cyclic silicates? After that, we have the fifth one, which is our two-dimensional silicates. In the case of the two-dimensional silicates, what you need to remember is all 3 oxygen atoms are shared. All 3 oxygen atoms are shared. All the 3 oxygen atoms are shared. Okay, you need to remember this. Even there is a structure I have made for you. This is your pyro. This is your pyrosilicate. This is your cyclic silicate. Okay, this is your cyclic silicate, but with some more silicon atoms. After that, we have the chain silicates like this. Pyroxene, Why it is called as pyroxene? Because you can also connect this chain like this also. If you connect this chain like this, if you connect this chain like this is only a one line sheet as a chain. If you connect one more line above it, it will be called as amphiboles. It will be called as amphiboles. Okay. So if you have only this much part, if you have only this much part, it is called as the pyroxene. But if you have whole of this part, it will be called as the amphiboles. It will be called as the amphiboles. If you want, I can make whole of the amphiboles. Okay. I think I need to make something smaller. Like this. Okay. So it's a two-way sheets going on, that will be called as the amphibole. Okay. Again, if you want to extend like this, I can make it, because I'm not stopping over here, because sometimes you get confused with this. So I have extended. Okay. So this is your amphiboles and that is your pyroxene. If it is only the pink part, it is called as the pyroxene, and if it is the red part, it is called as the amphiboles. I have made a classification for you. Now we were discussing about the two-dimensional silicates in which all the oxygen atoms were shared. All the oxygen atoms shared, and the unit will be Si2O5 N2 minus. Okay, this much you should know about the silicates, which is two-dimensional. Simply you can, if you want to know the diagram, you can have a diagram also. I can make the diagram here itself. So you will have a connection over here also. You will have a connection over here also, and you will have a connection over here also. So all the three oxygen atoms will be involved in the bonding. So it is two-dimensional silicate. It will be a very big structure, so that's why I'm not making it, but you can understand. Then we have three-dimensional silicates. If you have three-dimensional silicates, one thing is very clear, that all oxygen atoms are shared. One thing is clear, that all oxygen atoms are shared. That is very, very clear. And the structure you are going to get over here is like this. All the oxygens will be connected to some other group because it is a three-dimensional silicate. So you need to understand the fact that how many oxygen atoms are shared in the orthosilicate? There is no oxygen atom shared. Pyrosilicate, there is one oxygen atom shared. There is one oxygen atom shared. What about the cyclic silicates? Two oxygen atoms shared. Chain silicates, two oxygen. You should remember what is pyroxene and what is amphiboles. I have explained you. Next we have two-dimensional silicates. All the three oxygen atoms are shared. All three oxygen atoms. All oxygen atoms. If you want to have a quick in your notes, so you can write over here 3 oxygen shared, and here you can write 4 oxygen shared. Even they can ask you, if 3 oxygen is shared, how many number of oxygens are left which will give you the charge? Only this much will not be connected. Only this will not be connected. So it will give you the charge. Okay. That's why you have a negative charge present. Here you will not have any negative charge. This unit is simply called as the SiO2 unit. Simply called as the SiO2 unit. Even I can show you the structure of this also in a short manner. They even ask you how many number of atoms are present. 1, 2, 3, 4, 5, 6, 7, 8. It's a 8-membered ring. If you have 4 silicon atoms, it is 8-membered ring. Sometimes this question can also come. If you have 4 silicon atoms attached with you. So there are 8-membered rings formed in this structure. Okay, beta? So we are done with the chapter P block elements. Start solving the questions of the P block elements, refer your NCERT and any of the examination of your NEET and JEE, and all the best. Thank you so much.